I would like to welcome everybody for our 24th annual JB Douglas Postgraduate Awards. We have a pretty packed afternoon, but thank you very much to come today and to support the students of our universities and departments. So it's very, it's great to see so many people. So let me start by saying that I would like to begin by acknowledging the Gadigal people, traditional custodians of the land on which we meet today, and pay my respect to their elders, past and present. I extend that respect to Aboriginal and Torres Strait Islander people here today. So as I said, we are here to celebrate our students with the JB Douglas Award. JB Douglas is one of our main events as New South Wales branch of the Society of the Statistical Society of Australia, and it's a way to provide a platform to showcase the depth, breadth, and excellence of our students. And it's named in honor of Associate Professor Jim Douglas. We would like to thank some of our, like all of our sponsors who made this day possible, in particular the Statistical Society of Australia and the Australian Bureau of Statistics, but also departments and schools throughout, like in New South Wales. So we have UNSW Data Science Hub, Macquarie University, UNSW, the University of Sydney, the University of Wollongong. There, Western Sydney University, School of Mathematics and Statistics and Business School of the University of Sydney, UTS. So what we're going to do today, we have, as I said, a pretty packed program with 5 presentations in the first half. Then we'll have an afternoon tea that is offered just outside this room. And then we will have 5 more presentations. Then there will be a light refreshment at the end, which gives the judges time to deliberate. And we'll end up with the winners and the ceremony. So our presentations will be judged on the originality of the work. So it's a bit more about the content of the PhD thesis, on the impact in the sense that the candidates should be able to describe the impact. That could be an applied impact or a theoretical impact of their work. So it could be any type of research areas within and outside academia. We'll also judge the quality of the presentations. Remember to be on time. I will give you signals for when 5 minutes are left, 2 minutes are left, and when you really need to stop. I'll be sitting in the middle table, so try to look at me when I give this. And then, so the presentations will last 15 minutes, and then there will be 5 minutes of questions from all the audience. So the judges include myself as president of the New South Wales branch of the Statistical Society of Australia, and then we have Professor Sally Cripps from UTS, who is also our annual lecturer at the end of the JB Douglas presentations, and thank you for joining us. And Professor Yannan Fan from UNSW and Data 61. So again, thank you Yannan and Sally for joining us today. As I said, we'll give the awards presentation at 6, and then we will have the annual lecture. And after the lecture, we will have the annual dinner with the traditional trivia. So again, thank you very much for joining us today. I hope you will have a nice afternoon, and I hope in particular that our students will have a nice afternoon. I know that giving public presentations is always difficult, but we are here to support you and to share the happiness with you. So in a way, you're all winners because you've been selected by all the universities already. So we don't want this to be like a competition really, but just a way to celebrate all your work during the last few years of your life. So I would say that it's time to start. And our first speaker of the day, I would like to say one more thing since I have time. So I would like to thank all the council of New South Wales, of the New South Wales branch. This is an event that has been organized by all of us. And there is a person that did a lot of work. So let me thank Kevin Wang, without whom this event wouldn't have been possible. Thank you very much, Kevin. And also Nicole, who is our secretary, and she started the organization, but now she's in maternity leave. So exactly. So let's thank Nicole and Kevin. So the first speaker of the day is Paco Tsang, who is from the University of Sydney Business School and there. So I have to stop sharing. Yes.
You don't have to stop.
I don't have to stop sharing, sorry. I think they're all together.
You can just keep sharing the thing. You just need to exit this one.
Oh, they're all together, sorry.
Yeah. And Paco can open this one up.
Is it like, you can just
You have to stop your thing.
Someone else has a clicker, but I don't think, I don't think this is it, but you just press, just press the arrows.
Yeah.
Do you want to just click through and just make sure everything's fine?
Well, I'd still like to change anything. But yeah, I hope it's fine. Yeah, I believe it's fine. Yeah.
Okay, sweet. Okay.
Good luck.
Thank you. Good luck.
Do I wait for the signal to start or I just start?
You
can start.
Hi, good afternoon, everyone. My name is Paco, and I'm very honored here to be as the nominee of Business Analytics Research Group of the University of Sydney. And here today I'm talking about some more on variational Bayesian computations. And so this is the joint works with my supervisors Minyok and Long Nguyen, who is a professor at the University of Michigan. So what am I talking about today is we're proposing practical Bayesian computation that's alternative from MCMC, and it combines the merits of both MCMC as well as variational inference, and we are here to also provide the theoretical guarantees of our proposed method. And the whole thing is inspired by Jacob schemes, or it's what you call the Wasserstein's gradient flow. Cool. So let's talk about some of the motivations why we're doing all this, right? So in the modern era of machine learning, large scale inferences becomes increasingly important, right? So what that means is we need fast and scalable methods, okay, to approximate a very complex posterior distributions. And here we're going to going forward, we're going to refer this as the target distributions, because we want to emphasize that it doesn't have to be a posterior distributions. We can use this method for any complex distributions that needs to be approximated. And why VI? It's because it is fast and scalable. And what it does, it's an alternative to MCMC. So it reformulates the problems, the approximation problem as an optimizations problem. And with the KL divergence as the objective, and the optimizations is conducted over your proposed family distribution. So when these family distributions is simple, and then your optimization becomes very simple. So hence fast and scalable. And of course, this leads to potentially poor inferences of your approximations. And our contributions here is we want to bridge the gap between MCMC and variational inference via the Wasserstein's gradient flow theories, okay? And in addition, we're going to provide the convergence analysis for our proposed computations, okay? So here, I think I'll try to, right. So way to hide this? Oh, here. Yeah, there you go. Here, I'm just going to quickly provide a motivation example. So this is potentially, the one in the middle is the contour plots of our targets, okay? And you can see that it's a mix, it's a Gaussian mixtures, 4 very separated models, and our result is we start from the things on the left most, which is initial particles, we have a size of, or we have a point cloud of size 1000s. And going through our methods, we move the particles into the thing on the rightmost. You can see that resembles of our targets, okay? And the things we want to point out is that these examples is particularly challenging to be approximated using conventional MCMC methods, right? Because you can potentially get stuck on one of the clusters, okay? And cool. Oh, what happened? So then here's a bit of the background, the key concepts of my research. So it intertwines 3 areas of research: the variational inference, which is the main motivations, right? It's we need a fast and scalable practical Bayesian computations. So that's the whole motivations. And the Wasserstein gradient field theory provides the background of the theory for us to bridge the gap between MCMC as well as and variational inference. And the convex analysis provides the additional theory for us to reformulate the optimization problem to become practical, and it enables us to study the properties that guarantees convergence. Okay, cool. So here, let's go into the actual more dense theory. So here's the background. What is Bayesian computations? So suppose that we have a target that we only know up to the normalizing constant, okay? Currently, there are 2 largely favored approaches, and for different reasons, okay? One is what we call the well-known Markov chain Monte Carlo, MCMC. So what it essentially does, it carefully constructs a Markov chain that it asymptotically samples from the target's distributions, okay? And highly relevant examples is the Langevin diffusions. Okay, the MCMC algorithm is called Langevin's Monte Carlo. So what it does, you have the particles that follow this dynamics, and eventually you see samples from your targets. And variational from the other side, what it does, it proposes a simple or more tractable family of distributions, and within that family, you optimize it, and you use that optimizers as your approximations to your targets. Cool. So what are the different reasons why they're largely favored? So MCMC, it offers theoretical guarantees. Okay. So if you let the algorithm run sufficiently long, you will get it converges to the targets. So the 2 keywords here is being long, means that it's time consuming, and sufficiently we currently lack of a well-defined metrics to assess the convergence. Okay, so we don't know when to stop. All right, and VI, although fast and scalable, if your proposed family of distributions is very simple or too simple, you will get very poor inference. So the question is now, how do we combine the merit of both 2 methods, right? So we want the variational family to be flexible enough. So how flexible? What we said is we look at all continuous measures that has the second moment finite. Okay, that's relatively well inclusive. And in this space, do we still have theoretical guarantees like MCMC does? And 2, do we have a fast and scalable optimizations methods? Okay, and how do we do all this? The answers we'll provide later, but that's what is the theoretical guarantee offered by MCMC. So using our examples, the Langevin diffusions. Okay, cool. So if you move your particles according to these things, the first thing is the potential field or the drift where you're going, and the second term sort of mimics the random disturbance you have, which is this randomness. And what it says that is the corresponding focal Planck equations, which is the equations that governs the evolutions of the distributions of your particles follows this. Okay, cool. So this is what we have from MCMC, starting from Langevin. It goes to have a focal Planck. Right now, can we bridge the gap of VI? So VI, this is a problem we want to solve, right? And if your variational family is very, very flexible, like the one we proposed, it's very difficult to solve. And so the solutions is we have a time discretization scheme. So what that does is we solve the initial value problems, right? So what that does is starting from somewhere, I want to go to the minimizers. But not only I care about the minimizer, I care about the curve that goes from your initial value to your optimizers. Okay, and these, when you don't have the gradients or the stuff available, these is sort of for some of the people, it's what we call the proximal gradient methods, right? So following this time at every step, so what you can see, the first term, it's still our objective, the KL divergence. And the second term is sort of penalizing how far you can look around your neighborhood, and you go into that, okay? So this term is, so this scheme is termed the JKO scheme, named after the three mathematicians that provided all the theoretical results of this thing. So why do we care about this? Is because that, suppose that you have the sequence of the JKO solutions, right? The sequence that you just solved using the JKO schemes, and you interpolate it properly, well, in particular the displacements, interpolations. Then you take the limiting of this curve, which means that the tau, your step size, goes to 0. It behaves as the Wasserstein gradient flow of the KL divergence. Okay? And what does this mean to us? Is that this curve also converges to the solutions of your Fokker-Planck equations of the same Fokker-Planck equations of your Langevin diffusions. Okay? So these is now, we have the connections, right? Coming from VI, using the Wasserstein's gradient flow theories, we could reach the Fokker-Planck equations going from Langevins. The corresponding corresponds to the same exact Fokker-Planck equations. Cool. So now that's it, right? That's a very nice theory. It bridges the gap. How do we make it practical? Okay, we relies on the Brenius and McKean's work. Okay, we can reformulate the problem, optimization problem, on the space of problem measures to be on the space of convex functions. So this is what it does, right? So we're solving the same thing, except for notice that the optimizations happens instead of over the probability measure space, it's now on the space of all convex functions, okay? And those things are just the push forward measures of your the current probability measures that you have, and you look for the push forward measures, okay? But this is almost practical, okay? Why I said almost, because we're not talking about how you compute the mapping. We're talking about, suppose that they're readily available, what are the results do we have, okay? So notice that we have a bunch of particles, we move it, supposedly that we have the optimal mapping, okay? We're just pretending we do. What are the results, okay? And now, for us to have any theoretical results, we require some of the assumptions, right? And the assumptions are on the potentials, which is implicitly on your target distributions. So these are just to ensure that we have a unique, okay? These are not very strong assumptions, okay? And the result is saying that following that, our proposed almost practical particle floats, variation inference, at every iterations it minimizes, okay? So your next steps is has a smaller objective values than your previous steps, okay? Furthermore, if you further say that your target distributions is strongly log concave, which means your potentials is strongly convex, then you have a stronger result, okay? Not only that, it's saying that if we let this result, that this algorithm runs long enough, we have the KL divergence to the targets goes to 0. And we know that the KL divergence is 0 if and only if the two measures are equal, right? So we have this very strong things that it converges to the targets, okay, if we let it run strong enough. Cool. So, and that's done for the almost practical ones. What's the actual practical ones, right? We acknowledge that you never have the optimal mapping. You have an estimations versions of it. Okay, so notice that the algorithm here is the same, except for that we acknowledge that these optimal mappings are estimated using your empirical measures of your current particle locations. Okay, and there are ways to do that. We propose a typical methods called using the normalizing flow, and we will further talk about that a bit later. But just suppose that we can estimate this, okay? We put conditions on how good our estimations are, okay? And those assumptions of our estimations comes from very, very similar to the ones in the study of stochastic gradient descent, okay? Very similar assumptions. It ensures that we can control the optimality gap, okay? Thank you. And that's it, right? So our objective function of the K divergence or to the target goes to this if we let it run sufficiently long enough. And these the things on here are just constant terms of your assumptions, and this is controlled by your step size, right? Cool. So we also have the results for diminishing step size. This is for constant step size. For diminishing step size, we have a stronger results. Then that's it. So what's the main takeaway of today of my research? Now, we use the Wasserstein's gradient flow to bridge the gap between MCMC and variational inference. And then we propose a practical Bayesian computations that we what we call the particle flow variation inference, right? And we give you the convergence of the theoretical guarantees under some regular conditions that we for both constants and diminishing step size. Okay, and we demonstrate via examples that MCMC is challenged to do so. And what we do is now, how do we do that? And the method is called the convex gradient normalizing flows. We can use this normalizing flow to flexibly estimate the map, okay? And not all normalizing flow mapping or the resulting are a gradients of a convex functions. So we further restrict our normalizing flow to accept this such that the Jacobians of the mapping is symmetric and non-negative, okay? So that's it for today's talk, and I'll finish with another examples to demonstrate that our methods, where MCMC is available, the results are on par. So you cannot see the distinctions between the two results. MCMC is the solid lines, and the dashed lines is our proposed J-curve. Cool, and that concludes my presentations today. Thank you very much.
Thank you, Parker. Do we have any questions? I think the easiest thing to do is if you ask a question and then you may repeat it for the audience online.
Sure.
If you, or I can repeat it. So, do we have any questions? Yeah.
Thank you very much for a lovely talk.
Hi, Sally.
Look, you're motivated with a mixture of Gaussians and forums, and so I suppose my question, I've got two questions, which is, you're sort of comparing it to vanilla in CMC, whereas there are many ways in CMC, such as parallel temporal around those. So you thought about how does your method compare to that? That's question one. And question two is, do you require even though they're far apart, do you require gradients to exist? What happens if they don't?
The gradients so that's one of our assumptions here. Here, we require the potentials to be second differentiable. Yeah. And yeah. So we do. And right now, if we also require the targets to be absolutely continuous, otherwise the whole thing doesn't work. So that's your second question. Is there a third one? Cool. All right. So do I repeat the question?
Summarize. Like, actually, I don't.
So Sally asked, for these typical examples, do we compare it to other more modern MCMC? Yeah, of course. That things can get around how to this and have we? Not yet. And one of the things of why we say this is better is that we can actually assess the convergence, right? It gets to a point where our particle, we can actually estimate the K divergence and say that it's within the threshold that we're acceptable and we can stop. And I'm not sure, I'm actually.
It's fast too.
Yeah, much faster. Yeah.
Yes, because when the governments, that our vision, you cannot jump from one level to the other with a chance.
Yeah. So yeah, and there's everything of our particles we can treat as parallels, right? Yeah. So.
I guess it would be more fair to compare to sequential Monte Carlo because that's more designed to actually capture modes. Have you compared to that?
No, not currently. Yeah. So.
Any other quick question? Yeah.
It wasn't.
Just one of the, I'm just confirming if this is indeed an advantage of this algorithm. So I suppose like things with like what sounds like parallel tempering, that still require a bit of sort of sophisticated tuning with XMC to actually get it right. And then even if you sort of get it to jump within the modes, you might not necessarily, I think, get the weight of the mixture correct, because everything might start one mode for particularly longer, and if the energy that requires to jump between these modes is not sufficient, then you might not get the weight. So does your algorithm get away with that problem? Like, you know, because it looks like we do get the weight right in this case because the modes are equally weighted.
Yeah, there's also a bit unfair, like in a way, like you can see that the initial position is literally in the center.
Yeah,
so,
that's
like
right.
yeah. So you move that. So it actually depends on your initial positions. It could potentially go there. And so what we do is that if you can make your initial ones be large enough, or sorry, widely dispersed enough, then and that can be yeah.
So you just put up the uniform, it'll be a reasonably.
Yeah. Hopefully, yeah.
Okay, let's thank Parker again. So our second speaker for the day is Virginia Head. Is it right there?
So you click the
Yeah.
Zoom. Yep. And yeah, you want to hide the person as well as the. Is it that one?
Floating.
Yeah. Okay. Yep. Why are they doing that? Oh, it must be your thing. That's
No, I haven't turned it on.
okay. Sure.
Okay.
Okay. Cool.
That's all. Okay, great. Thank you. And yeah, I'll give you the time and thanks for that.
Hello, everyone. My name is Virginia, representing University of Technology, Sydney. The topic is Bayesian generalized addictive model selection, including a fast variational option. This is my research project with supervision of Professor Matt Wong. Model selection techniques are very important to the large data sets. They can make the model parsimonious and are able to categorize each predictor's effect type to be linear, nonlinear, or zero. Our work is building on Chidachover and Hasty's paper in 2015. There are 4 key features in the regularization path approach. First is the use of the group lasso, which is the group list absolute shrinkage and selection operator. Second is the use of the Demarage spline basis to maintain orthogonal property. Third is the use of the regularization path. It has the attraction of obtaining a family of selected models along the path. If you want to choose a single model, then the cross-validatory selection needs to be used. In order to avoid the practical difficulties of finding the cross-validation minima and be able to traverse a bigger model sparse, we introduce a completely automatic Bayesian generalized predictive model selection methodology on the Gaussian and binomial response data with 2 approaches with our R package game cell base. We inherit the first 2 key features from Chidachover and Hasty's work, which are the group lasso and the Demarage spline basis. In our Bayesian approaches, we use the Laplace zero family distributions as the sparse signal priors and the auxiliary variable representations to set up our full model. Second, we use the Markov chain Monte Carlo sampling, which is MCMC. Third, we use the mean field vibrational base, which is the MFVB, as the fast option to obtain the accurate and scalable generalized predictive model selection methodology. Scalable means that we can handle hundreds of thousands of sample sizes, with the number of predictors being 30, 60, or more than that. We use the misclassification rate percentage based on the actual and estimated effect time of predictors to measure the accuracy of our methodology. This is the generic form of the generalized addictive model involving the linear predictors. Based on this, we have this detailed form for our full model. X is the linear design matrix, contains all the binary and continuous predictors. Beta vector is the linear term coefficients for matrix X. Z is the Demarage form matrix. U is the spline coefficients vector for matrix Z. Gamma beta, beta tilde, gamma uj, and u tilde j are the auxiliary variable parameters. For the sparseness of coefficients, we use the Laplace zero family distributions for the priors. However, these distributions are not amenable to MCMC or MFVB So we use the auxiliary variable representations as this for the Laplace distribution and the group Lasso distribution. And we use other fundamental results as this to achieve that. Therefore, in our full model, the setting of the red part is to obtain the Laplace zero family distributions for the priors. The setting of the blue part is to obtain the half Cauchy distributions for the scale parameters. The top one is our likelihood function. We can use the directed cyclic graph as this to determine the full conditional distributions of the priors, which are the open nodes in white on this graph. They are all in standard forms for sample drawing in MCMC. For example, they are in multivariate normal, inverse Gaussian, inverse gamma, and Bernoulli distributions. If the response data is binomial type, this is the adjustment to our likelihood function. Based on Abel and Cripps paper in 1993, which is based on analysis on the binomial data, we introduced an auxiliary random variable vector C. This is the comparison of two directed cyclic graphs. For the bottom one, for the Gaussian response case, two nodes to the variance error, the sigma epsilon square and the A epsilon are disappear on the upper one for the binomial response case. On the upper one, vector C, corresponding to arbitrary auxiliary variable, is added to the position held by Y in the Gaussian response case. Before we move to the mean field variational base, here is the recap of the variational inference. The essence of the variational inference is search over for some set of the density functions to find out the optimal Q density functions with the minimum Kalbeck liable distance to the actual posterior by imposing product density restriction on the Q density functions. We take the auxiliary random variable parameter beta tilde as an example. Using the formula on the top, based on the full conditional distributions of beta tilde obtained in MCMC as this, we are able to obtain the Q densities approximations for beta tilde for MFVB as this. These are the examples of the optimal Q densities forms for MFVB. They are all in closed forms. Some equations of the optimal values are interdependent, so the iterations are required. We compute the marginal log likelihood at the end of each iteration. Once its relative error is lower than the tolerance level, then the iteration stopped. Based on the posterior distributions of relevant parameters, either the Markov chain Monte Carlo samples or the mean field variational Q densities, we need the model selection strategy to decide a predictor is a signal or a noise to the model. Based on the settings of the coefficients as this, we are able to use the posterior mean of the gamma beta and gamma uj to decide an effect being zero, linear, or nonlinear. Tau is the threshold parameter between 0 and 1. If the posterior mean of both linear and spline coefficients are less than 1 minus tau, the effect is 0. If the posterior mean of the linear coefficient is greater than 1 minus tau, but the posterior mean of the spline coefficient is less than 1 minus tau, the effect is linear. Otherwise, the effect is nonlinear. The lower value of the tau leads to the sparsity fits, so we call tau as the sparsity threshold parameter. Let's look at the simulation studies for the choice of tau. This is the misclassification rate data of MCMC on Gaussian response data on 100 replication simulations. Each panel corresponds to a different combination of the sample size and error standard deviation as the noise level. For misclassification rate, the lower the better. Within each panel, the blue side-by-side box plots of misclassification rate are shown as a function of tau being different values. For low noise level, there is not much of a difference. For high noise level, with a sigma epsilon greater than 1, it has the advantage of having tau being 0.5 for lower misclassification rate. So the recommended default value of tau for MCMC is 0.5. Let's look at the case for MFVB. It has the advantage of having tau being 0.1 for lower misclassification rate. So the recommended default value of tau for MFVB is 0.1. Our R-package game cell base implements the algorithm of two approaches, which are the MCMC and the MFVB. We have the sufficient statistics of the input data as these matrices. They only need to be computed once and restored to be used repeatedly for our MCMC and MFVB. So we used the sufficient statistics matrices and the C++ implementation to improve the computational speed of two of our approaches. This is the comparison of the classification performance of our two approaches compared with the SPI-SLAP game on the Gaussian response data. SPI-SLAP game is another Bayesian generalized addictive model selection methodology. For the low noise level, they all have similar performance. For high noise level, our MFVB has lower accuracy. However, the computer runtime also needs to be considered against the lower accuracy. We'll talk about this in the next part. This is the case for the binomial response data. Both of our MCMC and MFVB approaches have better classification performance compared with the SPI-SLAP game. This is the comparison of the computer runtime of our two approaches compared with the regularization path approach and the SPI-SLAP game, with the settings as these for our simulation studies. Even though SPI-SLAP game is able to get a very good classification result, but it's comparatively slow and does not scale well to large data sets. Our MCMC approach took less than 3 seconds to complete 90% of the fits, and our MFVB approach took less than 1 second to complete most of the fits. This is the application of our R package on the actual data. The data is from the Federal Bank of Boston in the USA. 20 predictors, 14 are binary, and 6 are continuous. And the response variable is the indicator of whether a mortgage application was denied. The sample size is about 2,300. We use the MCMC approach in our R package. We issue the command game cell base with these arguments to obtain the fit object. Then we issue the command effect types of the fit object to get the result. 7 predictors were considered having linear effects. 2 predictors consider having non-linear effect, and 11 predictors having 0 effect. We issue the command summary on the fit object to obtain this table with the posterior mean and 95% credible intervals for all the selected linear fits. We issue the command plot on the fit object to obtain these graphs, showing these 2 predictors, the debt payment to income ratio and the loan size to property value ratio, having non-linear effect on the probability of the mortgage denial. The green shaded area corresponds to pointwise 95% credible interval, and the blue rows at the bottom of the plot show the values of the predictor. This is another application of our R package. 49 predictors in the data set, 44 are binary and 5 are continuous. The response variable is the indicator of whether a car purchased at the car auction had a serious problem of preventing it from being sold. We refer to such a car as a bad buy, and the sample size is about 72,900. We use MFVB approaches in our R package. 9 predictors were considered having linear effect, 1 having non-linear effect, 29 having 0 effect. It indicates that 59% of the predictors were discarded, making the selected models parsimonious. It takes 11 seconds to complete the model selection. In summary, for the three category generalized addictive model selection methodology, both of our MCMC and MFVB approaches and the effect type classification rule provide a practical Bayesian alternative to the frequentist approach. Both of our 2 approaches were driven by the high speed and the scalability to the large data sets. For the binomial response case, both of our 2 approaches have better classification performance compared with the SPI-SLAP game. For the Gaussian response case, below noise level, our MCMC has similar performance with the SPI-SLAP game. For the high noise level, our MFVB has lower accuracy. However, the improved computational time of MFVB and the scalability to the large data sets both need to be considered against the lower accuracy. Last but not least, in practice, the best approach to model selection depends on the size of the data sets and the time demands. Our paper is accepted by advances in statistical analysis. Our R package game cell base is available on CRAN for download and use. A vignette accompanies our R package game cell base with an illustrative example to explain how to use our R package in details. These are part of the references of our paper. This is the end of my presentation. Thank you for your attention.
Thank you very much. Do you have questions or opinions?
You explained how you selected that threshold.
For the threshold of the sparsity of tau, for MCMC, we have the recommended value is 0.5 according to this simulation study that we did. Because we obtained a similar results for the binomial response case. So for the limited space of the slides, we didn't put on the binomial response case, but they have very similar results. Of the simulation study that we choose 30 continuous predictors, 10 having linear effect, 10 having nonlinear effect, and 10 having zero effect. Yeah, because each set of the sample size, each combination, the different combinations of the sample size and the error standard deviation, we use 100 replications. 100 data set were used for each of this panel. And then for each of the replications, new generation of the generation involved the generation of the new coefficients. So these simulation studies are through 100 replications. We did change the data set. 100 different data sets were used in these simulation studies.
Exactly how you do. Do you put some aside and somehow find the correct tau value so that you get?
Yeah, we have the actual estimated effect type compared to the original effect type, so we can work out a misclassification rate percentage. We have a data generating function to generate the predictors. Yeah. And then we apply our R package just on the actual data, which are the two examples that I gave at the end of my presentation. For choosing the tau, we use the data that we generated from the data generating function that we created.
I just wonder why you don't put the apply on tau or optimize something over tau that have a more feasible way to select tau rather than.
We in our package we do allow the users to change tau if they like. So in order to make it a completely automatic process, we did the simulation studies for the best of the tau in our simulation study. But we do allow the users to change the tau. So once you obtain the fit object, you're allowed to have another update function that we provided in the R package to change the value of the tau.
Because when the answer question might be around why not make taus part of the parameters that you don't know when therefore
because we want to make it a complete automatic process, so that's why I think, yeah. yeah, we will consider it, yeah.
I guess the quick and dirty way would be to use some kind of cross-validation for the tau.
For the cross-validation, because for the game cell package, yeah, okay, yeah. We'll consider that. Yeah, that's a good question. Sorry, that's a very good suggestion. We'll consider it. Yeah, in the package. Yeah.
I think time to go on. But thank you for the question. Thanks for doing it. Our next speaker is Matthew Sensory. Now I need to do this. Sorry. Sorry, what should I do? Side loading meeting, yes. Okay. So Matthew is from the University of Wollongong. So thank you again. And again, I'll give you the 5 minutes. Thank you.
Hi everyone. Today I'm talking about neural Bayes estimators for likelihood-free inference. This is joint work with my supervisor, Andrew Zamit Manjon, as well as Rafael Huza and Jordan Richards, who are both at KAUST in Saudi Arabia. I'd also like to say thank you to my co-supervisor, Noel Cressy, for his supervision and his feedback of this work. Okay, so suppose that we're working with a statistical model that has a set of parameter vectors theta associated with it. Then, given data z, inference on theta usually proceeds with the likelihood function. But for many models, the likelihood is either unavailable because it can't be written down in closed form, or it's computationally intractable. And in these cases, one often uses what's called likelihood-free inference. And that brings me into neural estimators, which are neural networks that take data as input and provide parameter estimates as output. Their construction is very simple. You start with the prior distribution, sample many parameter vectors from it. Then for each of these parameter vectors, you simulate data from your model, and then you train a neural network to map from the simulated data to the corresponding true parameter vectors. Once they've been constructed with simulated data, they can then be applied repeatedly to real data sets at almost no computational cost. And for this reason, we say that they're an example of amortized inference. So the other key strengths are that they're, of course, likelihood free. They're very fast, so typically orders of magnitude faster than classical methods. And because they're so fast and amortized, bootstrap-based methods for uncertainty quantification are also extremely fast. This schematic gives just a basic idea of what these estimators are doing. So we have a neural network. The input is the observed or simulated data, and the output is the parameter estimates. So at the start of this project, we had 4 main questions that we wanted to answer. The first is, what are the connections to conventional estimators? The second is how to do uncertainty quantification when we can't do bootstrap sampling. Third, how do we deal with replicated data? And fourth, what do we do with irregular spatial data? So towards the first question, I'll give some background on some Bayesian decision theory. It starts with a loss function L that assesses an estimator for a single parameter vector and model realization. Then the so-called Bayes risk averages this loss function over the entire parameter space and sample space. And it's given in equation 1, this double integral. Any minimizer of this Bayes risk is then called a Bayes estimator. So returning to neural estimators, let's denote one by theta hat gamma, where gamma are the neural network parameters. These are typically called the weights and biases in the machine learning literature. Then the construction of neural estimators that I described a few slides ago essentially boils down to this optimization task given in 2. Here we're selecting the neural network parameters that minimize a Monte Carlo approximation of the Bayes risk. For this reason, the neural estimator is approximating the Bayes estimator, and we refer to them as neural Bayes estimators. This connection has a couple of useful results. So first, we can start thinking about the properties that neural estimators will inherit from the Bayes estimators that they approximate, such as consistency and asymptotic efficiency. We can also control the behavior of our neural estimators by choosing the loss function appropriately. So for example, if we train the neural Bayes estimator under the L2 loss, we know that it will approximate the posterior mean. This connection to Bayes estimators is then useful for answering our second question on uncertainty quantification, because the Bayes estimator under the loss function 3 is actually the vector of marginal posterior quantiles. So by training a neural Bayes estimator under this loss function, we can then approximate any marginal posterior quantile that we want, and we can use this for uncertainty quantification through the construction of credible intervals. And these credible intervals are then have all the properties of neural Bayes estimators, namely likelihood-free, amortized, and fast. The connection to Bayes estimators is also helpful for dealing with replicated data. So here we're talking about a situation when we have M replicates, Z1 through to Zm. And so we actually showed that the Bayes estimator is invariant permutations of these replicates. So if you change the ordering of the replicates, the Bayes estimator will give you the same estimate every time. And so what we decided to do is to explicitly enforce this property into our neural network design. So the way we enforce permutation invariance is through what's called the deep sets framework. And it's given in equation 4 and illustrated in this schematic, which I'll focus on. So the way it works is you have your M independent replicates, and each of these replicates are passed independently into the first neural network, which we call psi. This will then result in a set of M transformed feature vectors, which are then aggregated into one single vector by the aggregation function A, which is usually just a very simple function like the element-wise mean. This will then give us a single vector, which you can think of as like a summary statistic of the data. This statistic is then mapped into parameter estimates by a second neural network phi. So you can think of this construction as a nonlinear mapping of summary statistics, where the summary statistics are learned automatically by the first neural network. So the other key properties of this architecture is that M is arbitrary here. It doesn't matter whether you have 10, 20, or 100 replicates in your data set. You can use the same neural estimator, irrespective of the size of your data set. The second key property is that this deep sets framework is actually a universal approximator for permutation invariant functions. And since Bayes estimators are permutation invariant functions, an estimator constructed in this form can theoretically approximate a large class of Bayes estimators arbitrarily well. So finally, we wanted to deal with irregular spatial data, which is often encountered in practice. And to do this, we use what are called graph neural networks. And the trick here was to view the spatial data as a graph with edges weighted by spatial distance. The main advantage of this approach is that G&M-based estimators can be applied to data measured over irregular spatial locations. They're parsimonious because they explicitly model spatial dependence by a generalized convolution operation, and they're not tied to a specific set of spatial locations. So a single G&M-based neural estimator can be reused over and over again on different spatial data sets without having to be retrained. So now I'll talk through a few simulation results. The first model we considered is the spatial Gaussian process with two parameters, a noise parameter and a range. We have 250 observations on the unit square, and we used these priors. The total training time was a bit over an hour. The main motivation for choosing this model is one, it's a ubiquitous model in the literature, and two, the full likelihood function is available here. So we can compare our estimator to the gold standard maximum likelihood estimator. This figure is showing 4 spatial data sets in the top row with different spatial locations. And then below each of the spatial data sets are the marginal sampling distributions for the noise parameter tau in the first row of box plots and the range parameter rho in the second row of box plots. And the green box plots are our neural Bayes estimator, and the gold box plots are the maximum likelihood estimator. And so the main takeaways from this figure are that the G&M-based neural Bayes estimator can clearly be applied to spatial data sets with different spatial locations. And the sampling distribution is relatively similar here to the maximum likelihood estimator. And that's reflected by having a similar root mean square error for both estimators. And so for this model, the main advantage of using the neural estimator is that it's substantially faster. It's over 600 times faster in this case. The other result that I wanted to report is that we tested the quantile approach to uncertainty quantification I described in question 2. And we found that its empirical coverage was close to the nominal value of 95%. The second model we considered is called Slater process. This is a max stable model used for the analysis of spatial extremes. It's also got 2 parameters to estimate. And the main reason we chose this model, thank you, is because although the likelihood function is known in closed form, it's computationally intractable. So what's often done in practice is a composite likelihood approach called the pairwise likelihood estimator. And this is the one we use for comparison here. So this figure is similar to the one I showed previously, 4 data sets again. This time, you can see that the neural Bayes estimator in green has a much lower sampling variance than the pairwise likelihood estimator. So it's a more efficient estimator in this case. And that's emphasized in this second plot. This is showing the root mean square error as a function of the number of independent replicates. So that's the number of spatial fields that we're doing inference with. And you can see that our neural Bayes estimator is a uniformly better estimator than the estimator based on the pairwise likelihood. So it's substantially more accurate, but our estimator is also substantially faster. In this case, it was over 5,000 times faster than the pairwise likelihood. And so I think this is a really great example that emphasizes that this new technique is a substantial improvement both in accuracy, but also computational performance, what was done previously. So we considered an application on global sea surface temperatures. So we were analyzing data collected from the Suomi NPP weather satellite. And to deal with non-stationarity, we partitioned the spatial domain into this grid that you can see on the right-hand side here, and performed a local moving window approach where we fit a different Gaussian process model within each cell. So in total, there were about 2,000 Gaussian process models that we had to fit this analysis. Yeah. And yes, so this figure is showing the resulting point estimates in the top row. We've got the range parameter in the top left, followed by the marginal variance, and then the noise parameter. And below, in the second row, we have the corresponding credible interval widths. And these were both generated with the neural Bayes estimator. And so these 2,000 models were fit in just 3 minutes with our neural Bayes estimator. And just to give you a sense of the scale of this estimation task, each of these 2,000 cells had, on average, 9,000 spatial locations to estimate with. So the fact that we can do it in just 3 minutes is, I think, really a great demonstration of how powerful this framework can be and its potential utility. Okay, so today I've talked about neural estimators, which are a fast, amortized, and likelihood-free approach to inference. Thank you. We've tried to contribute to this field by linking neural estimators to Bayes estimators, proposing an approach to uncertainty quantification by approximating the marginal posterior quantiles, as well as proposing functional forms for handling replicated data and spatial data collected over irregular locations. We have a couple of software packages, one in Julia and an interface to the Julia package in R called Neural Estimators. Currently, the package facilitates the construction of neural estimators by the user, and our vision for the future is that eventually it'll also include a suite of pre-trained estimators that will allow the user to exploit this amortized nature of inference. We have further details in a couple of papers that are online. So the first is published with the American Statistician, and the second is on arXiv, if you'd like to check it out. Here's some selected references. And thanks very much for your attention.
Yeah.
Thanks for a very nice talk. I didn't follow. So you compared to a method that does some sampling from the posterior, or is it just like optimizing?
It's just like an optimizer of the likelihood.
Okay, so it's not that you get like posterior samples from one and only point estimators from yours.
No. So we just get point estimators for both methods. Yeah.
So have you thought about, because it's a Bayesian approach, right? So normally what's nice in a Bayesian approach is that you sample the posterior. You can use the samples to do like predictive inference, for example. Yeah. Can you do something similar with the output from this method?
So this method I spoke about today is really just designed for point estimation. You can target the full posterior distribution by having a quantile estimator for a large number of quantiles. But really, we've just focused on point estimation so far. There are some techniques in the literature based on like normalizing flows and that sort of thing that have similar properties to this framework in terms of being amortized and likelihood free that can also generate samples from an approximate posterior distribution. So, yeah. Thank you.
Thanks for the talk, very interesting. So do you have any intuition why the two networks, the two neural networks work better than just adding it more later for single neural network? I know this will not be result, but
are you talking about the replicated data with the deep sets?
that one, exactly.
This one.
So why we have to layer them?
Like two different neural networks. Yeah, thanks for the question. So the main reason for having this structure is if you just had a single neural network, it would be so if you had a single network that acted on all the data set at once, it would be restricted to data sets of a single size. So you know, like if you trained or constructed your neural network to act on data sets that had 10 replicates, you wouldn't then be able to use it for a data set with 11. Yeah. Thank you.
Another question?
But we have one.
Yeah.
So so everything but is depends on the network that you train at the beginning. How sensitive the findings, the outcomes are if you train the network at the beginning?
Like to the design of the neural network. So we didn't really do a lot of experimentation with the like specific architectures of each of these networks. We kind of just chose a neural network that seemed like to be like a reasonable choice. I think each one had about 100,000 parameters, and we tried it and it worked well, so we stuck with it. Yeah, it's it worked well. Like we assessed it relatively rigorously, but yeah, we don't think it's super sensitive. Thank you.
I actually had a question. So one way to have a distribution would be to use like a Bayesian network where you have like priors and series on the weights. But this, I guess, would increase the time a lot. Do you have an idea of how much, or is it doable?
No, I don't have much experience with Bayesian neural networks, so no, I'm not really sure. Yeah, that's an interesting thing we should look into though.
So I actually, like when you showed the first example, like with the Matern kernel.
Yep.
I was a bit surprised at the time. I may have, I thought like
This one?
So when you trained it, there was a 70 minutes.
Yeah, the training time. Yeah.
So I like it seems a lot.
So this training time mainly boils down to the fact that you're not training the neural network with the observed data set. So we're not like, you don't have a single data set and we're training the neural network on that. Instead, what you do is you simulate, like we sample maybe 100,000 parameter vectors from the prior and then 100,000 simulated data sets. And so it's really a very large training set.
And then when you apply your data set, it's just like portion of second.
Exactly. Yeah. 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 So yeah, it's one of the nice things about this framework is that a lot of application statistics are not really amenable to neural networks because the sample size is too small to train the neural network. But here, where we're training the neural network on synthetic data, we're able to use like very large expressive neural networks and then apply these neural networks in practice on small data sets. So.
Thanks obviously that you have quite restricted priors. Like how sensitive when you simulate data, when you simulate damage from the prior, and then you simulate data.
Yeah.
How sensitive is the estimation quality to the kind of variance of the
So because the Bayes estimator is just a functional of the posterior distribution, the sensitivity of these neural Bayes estimators, it really just depends on how sensitive the posterior distribution is to your choice of prior distributions. We generally take the prior distributions to be like uninformative, so here uniform, and to be as wide as possible so that you can reuse the same neural network on different data sets that have different properties. Yeah. Thanks.
Okay, thank you very much, Matthew.
So our next speaker is Isha Karoub. Right. They're coming. So yeah. No, I think you can do it. Oh, there was a question that I didn't read. I should read more. Sorry? There were more questions. Sorry, sure that we didn't ask your question. Okay, so where can I find it?
It's okay.
I think you can do it. No, I would like to have the best presentation you can have. Kevin is here. He's not.
Okay.
Yes.
Yeah.
Oh, it's here.
No, don't worry about it. I'll manage it.
Okay. You have to insert a password. Do
Yeah,
you want
I'll
us to, like, she would like to use Canva.
Yeah, you can log in now.
Do you want us to remove the
You have to-
screen? Like she's.
No, it's
saying-
fine. I'll just share it once it's on.
Just don't type your password if you want.
Bring my password.
Okay.
And please read the watermarks. No, we're not going to pay for it.
Yeah, but we need to share it on the
On the screen.
Zoom.
Oh yes.
You just share screen.
Yeah.
Just go to Zoom and
I'm
share
sorry, I'm
the
terrible with this thing.
It's
But
okay.
you were amazing. Yeah.
No, the
Just
first
this
one.
is clean.
First one will be the
Yeah.
screen.
This one?
Yeah, it's fine. Awesome.
Yeah, thank you, Isha. And again, like I'll give you the 5 minutes. Yeah. Thank you.
Awesome. Thank you so much. I have to give this disclaimer that my presentation is very different from all the other presentations because I'm from School of Business and that's how we do presentations, very, very different. My name is Isha. I'm from Western Sydney University School of Business. My supervisors are Dr. Michael Levin, Dr. Ala Khan, and Associate Professor Omar Mubin. And my topic is conceptualizing willingness to accept social robot recommendations in the hospitality industry. So we'll be conceptualizing a model and developing a scale to measure WASA, which is willingness to accept social robot recommendations. But before I start, let me ask you a quick question. Raise your hands if you've been in a situation where you go to a restaurant and you don't know what to order. Right? And then we ask the staff for the recommendation. And that answer to what do you recommend is more powerful than you may think. At that point, our judgment is clouded by peer pressure, aspiration, and marketing messages. So as organizations, as hoteliers and retailers, it's very important for us to know what really makes customers accept these recommendations. And if these recommendations are provided by social robots, which are very new, and I'll come to what they are, what impacts the acceptance of these recommendations? So before the technology, before everything, AI and machine learning, recommendations were provided by humans, still are. So they could be your friends, they could be your family, they could be the wait staff, they could be the customer service assistant. But as technology evolved, AI was used to provide recommendations. For example,
movies you may like on Netflix, people who like you bought these books, book recommendations on Amazon or in store as well. And as the technology has evolved further, social robots are also being utilized in frontline service settings. The global robotics market is expected to grow up to a value of USD $147.26 billion with a CAGR of 17.24% from 2017 to 2025. And they've been used to handle customer service queries. They've been used to provide clothing, movie, food recommendation, and as advertising agents. But first, let's understand what social robots and recommendation systems are. So social robots are these different kinds of robots that have a different entity. They are semi-autonomous or autonomous robots, and they can interact with humans by following socially accepted behaviors and norms amongst people they are interacting with. So the one in the middle where the man is feeding the cake, that's Pepper Robot, and that really encapsulates what social robots are. It's almost like you want to consider them, you want to care for them. When you're interacting, they're looking right at you using their modalities. They have gestures, like hand gestures they can use. There's one Pyro Seal, which is at the bottom, that can be used for dementia patients because it purrs and provides care to people. So social robots clearly are more persuasive as real humans or a video recording of a real humans, and users are typically more engaged and influenced with respect to other technologies. Researchers have also agreed that real robots impact engagement and human decision-making more effectively than a computer agent in a real-world environment. Now, what are recommendation systems? Well, recommendation system, as I mentioned before, could be provided by human beings or they can be provided through artificial intelligence. They're basically a salesperson who's highly knowledgeable about both the alternatives and the customer's taste. Most of the common recommendation system strategies are collaborative filtering method, which uses people like you would like this, so you should try it. It could be content-based methods that is using past data of the users, analyzing that, and then providing you with a recommendation. Or it could be hybrid method, which uses a combination of a lot of different methods and is most commonly used as well. They can be provided online, like movie recommendations on Netflix. Now, recommendations are super impactful. 54% of retailers claim that product recommendations act as key drivers of average order value in customer purchases. Shoppers who engage with recommended product had 70% higher conversion rates, and product recommendations can account for up to 31% of e-commerce revenue. They're a key decision-making variable in customers' decision-making. But we're really not really sure when these recommendations are provided by social robots, would they be accepted? And if they do, what factors impact them? So as a concept, willingness to accept social robot recommendation hasn't been studied. The measures for willingness to social robot recommendations are not adequate because they don't consider the customer's perspective. They're only looking at the robot modalities to understand how can we create better recommendation systems. The scales are not specifically designed for social robots, and as I discussed before, they are very, very different from humans and virtual agents and screens. There's very low clarity on what factors impact AI recommendations, and so we need to understand a little bit more about AI recommendation, and only then can we understand social robots. Essentially, the customer's perspective is missing. So my research examines what are the key drivers of willingness to accept social robot recommendation and how can we measure that willingness to accept. Through my literature review, I found concepts which were very, very similar to WASA or willingness to accept social robot recommendation. But as you can see, compliance really does not fit in hospitality context. You can't expect your customers to comply with your advice or your recommendations. There were willingness to accept AI recommendation, not suitable for social robots. There were recommendation adoption, but that was in healthcare settings. There were acceptance of social robot recommendation, mostly focused on system design and modalities, and then compliance with social robot advice. But what the great part of literature review, as you would all agree, is you can identify a lot of different things, like the factors that might impact that WASA. And the factors were attitude, subjective norms, IMI, inferences of manipulative intent, source credibility, and empathy. Attitudes are something that you learn through your interaction with people. Subjective norms are, if I do this presentation, what is everyone else going to think about me? Should they want me to accept it or not? Inferences of manipulative intent is, are you trying to manipulate me into taking a decision? Source credibility, how expert, trustworthy, and credible is this person who's providing me this recommendation? And then empathy is, are you empathetic towards the customer? So the research framework is, all those 5 factors impact willingness to accept social robot recommendation, and that impacts actual behavior. But the problem is, we don't know how to measure WASA. So in my study, I'll be developing a scale using Churchill and Tavalla's method that includes 6 steps. The first step is an extensive literature review. The second step is a thesaurus search. The third step includes expert panel interviews. The fourth step is exploratory factor analysis. The fifth step is confirmatory factor analysis. And the sixth is testing the model using structural equation modeling in AMOS. So the CFA and the EFA will be in SPSS, whereas the SCM will be in AMOS. So at the moment, I am in the middle of doing confirmatory factor analysis. For my research, the sample consists of undergraduate business students. It is going to be a 7-point Likert scale where we're going to be measuring the responses. Pepper robot that I showed earlier will be used in our study. The scales will be adopted and adapted from well-established sources, and fictitious brands will be used throughout the scenarios. For the 5 factors, attitude, subjective norms, IMI, source credibility, and empathy, we'll be using pre-established scale. WASA, we will be developing a scale. And for RA, recommendation adoption, a behavioral method of which one would you choose after the whole scenario has happened will take place. So in my scale development result, through my extensive literature review across IT, marketing, retail, hospitality, tourism, and healthcare, I was able to find 42 initial items that would represent WASA, and some of them were attitudinal about their experience, and some of them were more behavioral, that if they accept, I will, if they recommend, I will accept or not. And that is what I hypothesized. Second was thesaurus search, through which I was able to add 12 more dimensions, and then those 62 items, were put forward to the expert panel to assess the content validity, which is testing if the scale measures what it is supposed to. So expert panel consisted of 5 members, 3 males, 2 females, aged 25 to 44, with educational backgrounds from bachelor's to PhD. It was conducted online, and they were provided with a definition of social robots, operational definition of WASA, which is key, explained the purpose of the panel interviews, and they were asked to imagine a scenario where they visit a fine dining restaurant, they come across a social robot who then provides them a recommendation, and then they rated the items that I had developed for measuring WASA. After rating the items, they engaged in a productive discussions about the clarity, readability, and content validity of those items. There was no agreement on the word compliance, as I mentioned before, because it does not fit the hospitality context. Between the words try, use, and accept, accept was found to be more representative of the construct we were trying to measure. Items were then combined, removed, or revised to fit the WASA scales, and any items that were not considered representative were removed, and total 12 items remained in the initial pool of items. With the expert panels agreed that some were drivers and some outcomes, which aligned with my earlier hypothesis that this is some of the items are behavioral and some are more attitudinal. So exploratory factor analysis was conducted with undergraduate business students in a pilot study. They were asked to imagine that they're in a fine dining restaurant. We brought in the social robot. It provided them with a recommendation, and then they completed the online Qualtrics survey, which was anonymous, voluntary, and confidential. We collected 118 responses, and after completing the data cleaning process, we were left with 99 responses, which was considered adequate for this factor analysis. For EFA, the KMO was good, but immediately I knew that there were 3 dimensions that were bidimensional, making the scale bidimensional, but it should have been unidimensional scale. And those were 4, 7, and 10. Those were negatively worded items that had to be recoded. So WASA 7 was removed because of double loading, and then another exploratory factor analysis was conducted. It still was loading on another dimension, so I conducted a reliability test to check the alpha, and if I delete some of those items, whether my scales measurement will improve or not. Clearly, if you can see in the red circle, if the items were deleted, the Cronbach's alpha would go to 905 and 908. So I started with WASF 4, which showed some improvement. Once I did that, it still said that you should remove WASF 10 because it's going to improve your measurement and your scale further, which I did, and it improved the Cronbach's alpha to 0.926. And Cronbach's alpha, if it is more than 0.7, is considered very, very good. So this is excellent. Just to confirm my scale and just to make sure that measurement was all good, I conducted another factor analysis. It gave me 0.876 KMO, and KMO, if it's 0.6 and above, is considered very good. So 0.876 is really good. It was significant, highly significant actually at 0.001. Eigenvalues were all above 1 for the first factor, which is 5.730, and 63% of variance was explained by that one factor. All the factor loadings were above 0.5, even though the cutoff was 0.3 for the factor loadings, the factor loading was above 0.5. These are just the results of KMO 0.876, significant at 0.001, and Cronbach's alpha at 0.926. Then I conducted, these are pre-established scales, so I just wanted to make sure and do sanity checks. So all attitude, subjective norms, IMI, source credibility, empathy, all of them, the alpha and the KMO and the factor loadings were absolutely appropriate. Finally, I ran a regression test to test the whole model, and I could see that attitudes, subjective norms, and source credibility significantly impacted willingness to accept social robot recommendations. It was an IMI and empathy, which is a little bit surprising, but hopefully when we test it in another context, maybe in a cafe or in a hotel, we might find different results. Next steps are going to be confirming that analysis, a confirmatory factor analysis, and conducting a structural equation modeling in AMOS. So just finally, the study has huge theoretical, methodological, and managerial implications. It is the first scale in the field, and it will be the first empirical research to show that willingness to accept recommendation is actually impacted by multiple variables, and it is a strong indicator of actual recommendation acceptance. This instrument will be applicable across a broad range of industry, and as I move forward in the PhD, I will be testing it in a low involvement environment like a cafe and a 3-star budget hotel, as well as a high involvement environment, which is a 5-star hotel, to make sure that the instrument is actually applicable. It will help government in evaluating advantages and disadvantages of employing social robots in public spaces and take necessary steps to address worker shortages and provide retraining for industries facing high automation risk. Ultimately, integration of social robots will improve operational efficiency, increase cost savings, productivity, and enhance in-store experiences. There are some limitations, though, that we are only considering younger population. So future studies must extend this study and validate in new contexts such as retail. With older generation, more longitudinal studies should be conducted, and in different geographical locations such as Darwin, which is a little bit more regional area. But it is a new opportunity for businesses in regional and large cities for cost saving and for small businesses. Thank you so much for listening to me.
Thank you, Isha. Are there any questions? Yeah, Amanda.
Thank you for your talk. I was just wondering how do you plan to make the validity, given that the question who made in I imagine that what people answer it might be very different from what they experience in the so the validity issue.
Yeah, so that's one of the limitations, but also one of the strengths, because when you're using actual brand names to test what people behave like, it impacts their judgment quite a bit. It impacts their attitudes and impacts what other pre-interaction attitudes that they've had. So in literature, specifically in marketing literature, it is always recommended that you use fictitious brands. So nothing else matters, everything stays constant, and people can just look at how social robot is delivering recommendation and whether you can accept it or not. But that is something we always mention, that it is fictitious brand. So when before you actually deploy it in real life environment, you must test it.
Thank you for a really interesting talk. I'm curious though about just on the sort of related to the validity of things. In addition to measuring WASA, how do you go about determining or measuring things like empathy and attitude?
So we, for empathy, for all the other 5 factors except WASA, for which there's no scale, we are using pre-established scales. So we've got these theories which support all of those hypotheses. And then we've got these scale items that are from studies that have already tested these multiple different times. So these are pre-established scales. So for empathy, we have Pepper provides caring and individualized attention to customers. It does not give me personal attention, and all of them are measured on a 7-point Likert scale.
And these
Yeah, I know some of them are subjective, but yes, these scales have been used previously successfully. Thank you.
Yes, so I've never met a social robot before, and I expect that my response to a social robot the first time would be different than how I would treat it after 10 times or 100 times. Now, most people haven't met them, or most people haven't not yet used to them. So maybe the factors that affect my behavior now are different than the factors in the future when everything changes, when everyone already is used to it.
Yeah, I agree with you. And that's novelty effect. Like the first time you meet people or social robots, your impression is very different. And that's why one of the limitations is that it is one short-term study, and we need to do more longitudinal studies to understand how people continuously change their behavior. Would everyone else's behavior change as well along with them? But from what I've seen in the field, not social robots, but from more mechanical robots that bring out the dish to you in the restaurants, seems to be positive, but yeah, we need to do more longitudinal studies in future.
Very good question. So, given all of this, are you kind of mainly really measuring the recommendation acceptance rather than the recommendation acceptance? Right? To me, it's like it looks like what you're measuring is where people are going to accept it, not the robot. You're trying to encourage through the recommendation acceptance, but I guess in the actual moment of spending money, buying the things, etc., it's not so much that you can extrapolate that the recommendation will be what will be accepted. It's just really the medium from which the recommendation is from.
That's what we want to test. We want to test if social robots provides the recommendation, are you more likely to accept it, or you want to prefer a human being? And the point about spending is really good, because this one is a fine dining restaurant, which is expensive. You are really spending a lot of time, so you have to deliberate a lot more. Well, we are going to do a comparison study after model testing in SEM to see how people behave in cafes and whether that differs, whether the factors would differ and whether people's behaviors and attitudes would differ. And then we'll test it in hotels to see whether in those 2 different hotels, is it going to be different or not? Different types of hotels.
It's really for people who are really on site. What is the idea of, when you go and already know what you're buying, how much is this really influencing? I'm just thinking of the way you're monetizing, right? You monetize it just on the actual potential growth of the money, or just on the people who wouldn't have otherwise bought?
It's both. It's business. So you have to monetize on the opportunities that you have, and see if we can make people accept a lot more things, just like Netflix does. Do you want to watch this? Amazon does. Do you want to buy that? But it's also people who don't have an idea. Social robots can be very helpful. And because they're very human-like Pepper's eyes really blink, it really creates a very human-like interaction. So yeah, it's both. Thank you.
I don't think it's a question for you. I think it was coming from before, but I'll check more. Yes, sorry. You're very understandable, Shira. But I'll check more in the future, I promise. But let's thank Isha again. Where is my logout button? Why is my logout button here? No. No. Oh, there you go. Yes. Thank you. Okay.
Can I quickly just check?
the slide.
Yeah, just really briefly. I can just spam one or two of the slides. Only because they weren't appearing in one of the rooms I was testing it on. So just wanted to make sure that it's there. Yep, it's okay.
Okay, perfect. So I'll share it. And so, okay. This. Okay, so our last speaker for the first session is Jack Friesen from the School of Mathematics and Statistics of the University of Sydney. Thank you.
Thank you, Clara. So, hello everyone. Today I'm really excited to share with you some of the research that I've been doing, especially this last project I've been on with Lucas, Cal, William Noble, and Uri Kaif. And the goal of today's talk is to present to you a new method that allows you to combine any semi-supervised learning tool to the context of multiple hypothesis testing. So when we're doing multiple hypothesis testing, the objective is to report a list of discoveries, or if you prefer, reject a collection of null hypotheses. And we want to do this subject to the constraint that I want type 1 error rate control. That is to say less formally that I don't want to report too many false discoveries. So using these machine learning tools off the shelf without caution will certainly break this control. But we came up with a new procedure that allows you to use these machine learning tools and maintain that type 1 error control. So we specifically look at the false discovery rate, or the FDR for short, as that specific definition of type 1 error rate. So to motivate our new procedure, I'd like to look at a specific application of multiple hypothesis testing, and that is in peptide detection. So their machine learning tools have been used for like the last 10 to 20 or 25 years, but they're used in a sort of heuristic fashion. So it is possible, as we show, that using these machine learning tools can break your FDR control. And so to get there, I'd like to give you a bit of background on the canonical setup of peptide detection and what's typically done. So suppose you have a scientist and they have an unknown sample of peptides and they want to know what they are. This is with the broader goal of mind to learn the proteins that are in your sample, because proteins are made up of these smaller peptides. And once you have those, you can do so much more research like diagnostics, vaccinations. You can do protein-protein interactions, things like this. And so they want to know the peptides. And what they have access to is a database of candidate peptides, which they call targets. This is different to Paco's targets in the first talk. There's millions of these peptides. These are just short strings of amino acids. And some are going to be in the sample and some are not. And so what we're formally doing is testing a null hypothesis associated to each peptide, which states the peptide is not in the sample. And so to do this, I get my sample, or the scientist gets their sample, and they run it through a mass spectrometer to acquire all these experimental spectra. And from this, we score the peptides against this experimental spectra. So you might have scores like this. And the idea is the larger the score, the more confident we are that it's in the sample. The only issue is I don't know what exactly large means. That's because I don't have null distributions for each of these null hypotheses. If I did, I could plug these scores under the null distribution to obtain a p-value, and that would inform me. But I don't have that. So the next best thing that you can do is you can sample a single score from the null distribution in the following way. So what I want to do is I want to take my target peptides and shuffle their amino acid sequences randomly. And this forms these new peptides, which we call decoys. And then I can score them in the exact same way. So I might have these scores, say. And these scores represent a single score from their respective null distributions. And so what I want to do now is summarize some of this data. So I want to record for each target decoy pair the winning score W, which is the largest of the two scores, and the label L, which tells me whether it was a target or a decoy that had the higher of the two scores. So in the case of the first target decoy pair, I would record a value of 5.5 because that's greater than 2.3, and the label L would be 1 because it's a target. If it was a decoy win, I would record L equals -1. And so the idea of the decoys is that they're supposed to estimate the number of incorrect, or rather null target peptides that are not in the sample, right? And so that's because if I take a target peptide that's not in the sample and I look at its score, that's going to be from the null distribution by definition. It's not in the sample. And if I look at its decoy, the corresponding pair, we constructed it so that its score is from the null distribution. So if I look at these two scores, there's a 50% chance that the target will be higher of the two, or its corresponding decoy. So if I look at this quantity here, this is all the decoys that scored above some arbitrary score T. And that should roughly approximate the number of targets that scored above T that are not in the sample, that are null. And so using this approximation, I can estimate what is the proportion of incorrect targets above T. So that's this fraction here. The numerator is all of those targets that scored above T that are null. And the denominator is all of those targets that scored above T. There's the V1, just to handle the case when the denominator is 0, okay? And all I'm gonna do is simply just use the approximation I stated earlier to substitute out for that numerator. So I've just used that above statement to swap the numerator to the number of decoys above T. I'm just gonna do one last thing. I'm gonna add a +1 and call this FDR hat, which is a function of T. And this FDR hat, this +1 I've added, sorry, is there for technical reasons. It's because we're trying to do FDR control and not just estimation. But if you have questions, I can answer that. And this FDR hat is supposed to estimate the thing on the left, that proportion of incorrect target peptides. And so now I find a score threshold tau, which is the smallest possible score, such that my estimate is less than or equal to alpha. So alpha could be your nominal 5%. In proteomics, it's typically 1%, but and so once I do that, I'm going to report all the target peptides that have a score of L equals 1 above this threshold. That's my procedure. And so it's shown under very mild assumptions that doing this procedure, doing this reporting, that this procedure controls the FDR at level alpha. So what does that mean? The FDR is defined as this expectation quantity, which is simply the proportion of incorrect target peptides I'm reporting to. Right, so the numerator is all of those targets with a score above tau that are not in the sample, that are null, divided by all the targets that I'm reporting to that are above tau. And this is less than or equal to that 5% or that 1%, whatever you used at the start. So one natural question is, can I improve on my procedure and improve on W using some additional side information X? So W, if you like, is trying to score high the peptides that I want to discover, the correct ones that are in the sample, and score low the peptides that are not in the sample. And it might not be doing a perfect job of this. So perhaps I can improve on this using some additional information. So this side information could be the charge of the peptide, the length of the peptide, the mass of the peptide. There's a lot of data that you can use. And this idea is not new. This is done by what are called post-processors, which are just basically software that embeds some machine learning. And such an example of this is called Percolator. And this is a very popular tool. It has over 2,000 citations. And so I'd like to demonstrate roughly how Percolator works. It uses an iterative support vector machine. So what I have here is a plot of our peptides. I've color-coded them blue as targets, and in red, they're going to be decoys. On the horizontal axis, it's the score, W, and on the vertical axis, it's my side information, so maybe the mass of the peptide. And I would like to use the extra dimension, this side information, to report to you a larger list of target peptides that I want to report to you. Maybe something like this, say. But unfortunately, in the canonical setup, I'm forced to report to you this smaller subset of target peptides. So this is the picture where these are all the target peptides in blue that are above our score threshold tau. So how do we get from this to the picture before? Well, Percolator starts by fitting a linear SVM between the two classes using the decoys that I have shown here and all the target peptides above our threshold tau. So it does something like this. Next, it translates this separating hyperplane back such that the estimated FDR is still less than alpha. And then it uses these two new classes. Well, the decoys have remained the same as the negative set, but the new set of positive classes are made up of these target peptides, and we fit another linear SVM. And we do this some number of times until eventually we settle on some fixed number of iterations. And the last stage, we translate this back again and report all of the target peptides above this threshold. This is the general gist of percolator. But we show that percolator does not control the FDR. So there is these publicly available data sets where you have a good priori over the peptides that are in your sample. And because I know the contents of my sample, I can directly estimate the FDR extremely accurately. And so here I have my figure, which on the y-axis is that extreme accurate estimate of the FDR. On the x-axis, I have my desired threshold, for which I wish my y values to be less than. The colors distinguish different experimental setups. And as you can see, based off the identity line there, that if we were to have FDR control, these would be all bounded below the identity line. But instead they're not. In fact, at an FDR threshold of say 6%, I'm getting from the procedure a real actual estimated FDR of 9%, which is a 50% overshoot. So what can we do? There are some solutions from the statistical literature. So there is this tool called ADAPT. It's a general protocol that allows you to combine machine learning and FDR control, but you have to have p-values. And unfortunately, I don't have any, as I mentioned at the start. So we have to look elsewhere. There is this tool called ADA knockoff from this year, and it's a version of ADAPT when you don't have p-values. So that could be useful. The only drawback is that it's extremely computationally expensive. So if you want to ask as to why, please, the details are a little bit complicated. And the second point is that it uses, to be powerful, to report a lot of discoveries, it has some assumptions regarding the sign of information X and the winning score is W. This is not an assumption required for the FDR control, but just for a successful power boost in reporting the list of discoveries. And so it would be really cool if I could have the rigorous FDR control that ADA knockoff says has, but then have the quick efficiency that percolator has. And this is exactly what our new protocol reset does. You can combine it with any semi-supervised learning tool, but here I will demonstrate how it works with the percolator algorithm. And it begins by having all the labels masked. So I made them opaque to demonstrate that. And what we want to do is we want to go up to each decoy, flip a coin, and if it's heads, I will reveal it. And if it's tails, it stays hidden. So I have half of them sampled like this, yeah? And then the crucial step is that all the masked labels, I'm going to treat them as if they were targets all along. So we call them pseudo targets. And so using the percolator algorithm, I define a score threshold tau as we did before. And all of the masked labels that are above our score threshold tau will be the positive set for our training. And all the decoys that I have revealed are the negative set for our training. And then we fit a linear SVM. And we do the same thing. We translate this FDR threshold, this separating hyperplane back until the estimated FDR is less than alpha. And this reveals a larger positive set that I can use for my next iteration of my SVM. So I fit another one. And we do this again, some number of iterations until we've exhausted the number of iterations that we had started with. At this point, what we do is we throw away the decoys that were revealed. They've already been used for the purpose of training and are no longer useful now. And I'm going to reveal all the labels. Now, the last step, I want to push back this separating hyperplane once more, such that the estimated FDR is less than alpha, but I've thrown away half my decoys. So to make up for the slack, I have to double each decoy, because after all, they're estimating the number of incorrect targets, right? And half of them are gone. So now counting each decoy twice, I translate my separating hyperplane back, and I get to report all of these target peptides. So we show that under the same conditions of Barber and Candice in their original 2015 paper, as well as ADA knockoff, what I mentioned earlier, and ADAPT, that reset controls the FDR at level alpha. So those are the assumptions that they share as well. And we can verify this using the same experimental setup that we checked with percolator, where it failed to control the FDR. So that's exactly the picture on the right that I showed earlier. And on the left, we can see that all of these curves are below the identity line, indicating that our new procedure empirically as well controls the false discovery rate. Lastly, I wanted to verify that how reset's power compares to percolator. So what we did was we downloaded 20 biological real data sets from a public repository called Pride. And then I looked at the number of discoveries reported by research for a given FDR threshold. And I divided it by the number of discoveries that Percolator reports at the same FDR threshold, and took the quantiles across the 20 data sets. And as you can see, at the 1% FDR threshold, we get a value of 99%, indicating that we're 1% shy of the number of discoveries that Percolator produces, indicating that even though the Percolator cheats the FDR, it's remarkable that we're only 1% behind. At higher FDR thresholds, using the median, I should say, the difference is negligible. So that's nice. We have an extension that uses reset in a more powerful way that surpasses Percolator in the number of discoveries as well. So we have some further research. Reset can be used in arbitrary regression models, which is nice. And we can potentially regeneralize this to work with p-values in the future. Thank you. Yes, Michael.
Thank you. So can you talk a little bit about the password and the numerality? It's going through very quickly.
Yes, that's right. So I'm glad you asked that. So the +1, there's two reasons there's two versions I can explain. The proof version, which is probably the least useful one, is that it uses a martingale argument to get to this inequality. That's the worst of the two explanations. The intuition is that when we're trying to do this step here, the score threshold tau, I'm being greedy, right? Because I want to find the smallest score threshold tau for which my estimated FDR is less than alpha. That's favoring more targets than decoys. And I should say, when I have this score threshold tau, by definition, the hypothesis, the peptide that's just below the score threshold tau will be a decoy always. Because suppose it's not by contradiction, then I can lower that score threshold down a little bit more and reduce my score threshold. But I can't because of the definition of tau. And so what I'm really doing is I'm counting that extra decoy in my estimate. So I don't want to cheat myself by being too greedy and counting all these extra targets. Does that sort of answer your question? Yes, pretty much. In this case, the last one is always a decoy, which is, yeah, that's right. Yeah.
Really interesting. I was wondering, can you use this for lasso, doing transactional lasso?
After lasso, it can be used. So after lasso, I'm not sure, but it can use in replace of lasso. So the idea is that you can create decoys in this variable selection setup. So take the linear model as a simplified example. You can construct what are called knockoffs, which is the variable selection setting of a decoy. These are just like features that aren't in the model. And replacing these decoys for knockoffs, you can do a similar thing where you score your features and compare them to the knockoffs, and do all, as we said now, to report a list of features that should be in the model. And this will give you rigorous FDR control there. So there's this nice one-to-one correspondence between this target decoy setup and variable selection, which is why our procedure works immediately to I said at the end, it's immediately applicable to variable selection.
Yeah, that's exactly the setting I was thinking about. The question why we report without that. But sometimes we do.
Yeah.
I think it could do something.
Yeah. Actually, interesting. The canonical way that they score the features is that they use, the lasso path. They use the first time that the feature enters the model, and that's the score. So you can imagine that a higher score in this way means that it really should be in the model instead of the scoring that's done in this setup. Yeah. So thanks for the question. That was nice. Yeah.
Thank you. How sensitive is it to, you're doing a 50-50 split, or it's going to be really part of your support for the machine, or does it not matter to using the second spectrometer machine that brings back.
You mean,
Like when you're flipping, right? See if you.
you mean from here to here?
From there.
Yeah.
So obviously, you end up with all your decoys, let's say. Low,
Yeah.
Your threshold's
100%. That's a fantastic question.
But
Yeah, so I'm kind of really glad that you asked this because I didn't have enough time to talk about it. You can have an extension of this, which I mentioned earlier, where instead of one targeting with one decoy, you can have 2 decoys for every target. And so you can imagine if I do something like that, I'm going to have way more decoys to be used for training and then estimating the FDR afterwards. And there is an extension I want to do of this, which completely eliminates the randomness associated with sampling the decoys. And it uses something called E-values from the knockoff variable selection setting. So I'm not sure if this is something that you've seen, but it's really exciting. So it completely eliminates all the variation associated between how you select your decoys. Yeah.
Like just as a follow-up, I wouldn't imagine that the randomness is part of the setting for that.
So the reason that it works is that, so what makes it work is that the targets and decoys that remain here, so if I look at the decoys that I reveal at the end, because they're separate from the decoys I use for training, then a null hypothesis is like 1/3 going to be a target and 2/3 going to be a decoy. And so that's why it works. But in terms of it being better because of the randomness in terms of reporting list of discoveries, it would be really good if I could always promise you that my decoys are going to be representative of the distribution in the space spanned by W and X. So in your case, it could be possible that I sample all the decoys down here. And that will be bad because then when I'm doing my SVM learning, it's going to treat all the masked ones, which is like from here to the right, as if they were legitimate things I want to discover. But some of them are going to be decoys. So it's going to be not great. So that's like a pathological case, of course. But yeah.
Okay, so I'll just check if there is any question online that I don't know how to check. Is that right? Where am I? I don't think there is any question. Okay. Oh yeah, thank you. Okay, great. No more questions, so let's thank Jack again. And all the speakers of the first session. Now we have a break until 4:05, and we have a refreshment outside. So we'll start again at 4:05.
I want to test out the Zoom.
Yeah.
Especially we want to hear people. That's the main thing. So what I want to do is maybe try going to my
yeah.
I don't have. It's wonderful.
Do you want to?
Do you know what is the ring ID for that one?
Yeah.
Oh, actually, you should have it.
So it's 878 35 86 36 39.
Let me just check. Hello?
So you're talking.
Hello? Hello?
You're not talking.
You're talking, right?
Am I talking? Can you hear me? Can you hear me?
Yeah, but the thing is that the speaker needs to say things. So can you grant me like how to speak? Yeah, no, I got it. Let me go outside. I want to know if the sound can be broadcast. That's the main thing because. Can you hear me? Can you hear me? Can you hear me? Can you hear me? Okay. Testing. One, two, three, four. 1, 2, 3, 4. 1, 2, 3, 4. One, two, three, four. 1, 2, 3, 4. 1, 2, 3, 4. One, two, three. 1, 2, 3, 4. 1, 2, 3, 4. Hello, hello, hello. 1, 2, 3, 4. 1, 2, 3, 4. One, two, three, four. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. One, two, three, 4. 1, 2, 3, 4. I'm not hearing anything. One, two, three. See, I think that's my laptop speaker. Testing, testing, testing. Testing. Both of them are using my speaker.
Is that?
I think both of them are using my speaker. Testing, testing, testing. Testing, 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 testing. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. It's not even making sound now. It's a... Oh. Ah, that may be it. Hello?
Yes.
Hello? Hello? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. One, two, three, four, 1, 2. Hey, how did it work? 1, 2, 3, 4, 1, 2, 3, 4. Wait, it's too noisy. The room's too noisy. 1, 2, 3, 4, 1, 2, 3, 4, 1. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. Oh, it works. Okay.
Yes. And I remove this. Okay. And I do this. Okay. So welcome back. Our first speaker of the second session is Emma Yuan, who is coming from, is supported by the School of Computer Science at the University of Sydney and by DARE. Thank you very much.
Hello, everyone. My name is Emma, and my project focuses on structured learning and inference for Gaussian Bayesian network, which is jointly supervised by Professor Sally Cripps, Wang-Chuang Zhu, and Dr. Changlian Liu. So one major challenge in statistics is to formulate models and develop inferential procedures that is necessary to understand the complex relationship, multivariate relationship among variables of interest, especially in the context of high-dimensional data. And Bayesian networks, which combines graph and probability theory, represents a useful class of models for inferring the relationships and independencies. So by definition, a Bayesian network consists of a directed acyclic graph and an associated set of parameters, where each variable in the graph is considered as a random variable, and a directed edge between the nodes indicates probabilistic dependencies. One interesting property for DAC is that each variable are conditionally independent of the sets of its predecessors, given the state of its parents, and so we can write down the joint distribution of all the nodes as a product of conditional probabilities, each of which only depends on the parents in the graph. And what we're seeing here is a small illustration of a protein signaling network derived from multi-parameter single-cell data to better understand how protein signaling network modeling, sorry. And in Gaussian Bayesian network, each variable is a linear combination of its parents in the graph plus Gaussian noise, and the data is modeled as jointly normal with precision matrix omega and mean mu. So when the underlying DAC is unknown and need to be inferred from data, this is usually referred to as structured learning in graphical models. And as you can see here, the number of DAGs as a function of the number of nodes is super exponential in a number of nodes. And so traditionally, we do have to perform combinatorial search over a very large space of all possible graphical structures. And while traditional methods focus on recovering one possible graph or its markup equivalent, we predominantly focus on the Bayesian approach to structured learning, which aims to infer a full posterior distribution over graphs. And the main advantage of this approach, when compared to other methods that based on greedy searches or algorithms that focuses on optimization, is that it provides a collection of samples from the posterior distribution of the graph given the data. And that means that inference can then be made in the spirit of Bayesian model averaging, which is important in the context of high-dimensional data with sparse data. And we usually define the score for a DAG as its posterior probability given the data, where we place a prior distribution over the graphical structures, and the marginal likelihood can then be obtained by integrating out the likelihood function with respect to the parameter prior over the parameter space. So the first class of priors for model choice among DAGs, and is still widely adopted, is the Bayesian Gaussian equivalence score, which is proposed by Geiger and Heckman. So when the graph and parameter priors satisfy certain conditions on structure modularity, parameter independence, and parameter modularity, the score is decomposable, which has desirable properties for computational speed. And in order to facilitate this, we need a closed form solution for the marginal likelihood. And it has been shown that with the conjugate prior normal wizard on the joint parameter space of mu and omega, the score satisfied the above properties, which is extremely important for more advanced sampling algorithm in the context of Bayesian structural learning literature, such as order or partition MCMC that make use of order of the nodes and partition of the nodes. Recently, a more generalized class of priors was proposed with multiple shape hyperparameter that makes use of the modified Cholesky decomposition of the inverse covariance matrix omega. And here the matrix L is a lower triangular matrix with unit diagonal entries, where the off diagonal entries represent the negative edge weights. And the matrix D is a diagonal matrix with positive diagonal entries that encodes the conditional variances. So using the Markov assumptions, when an element ij in the matrix L equal to 0, that would mean that the graph doesn't have the directed edge from node I to node j. So given the positive definite matrix lambda, the shape hyperparameter, we can then write down the density of the DAG-Wishart distribution on the joint parameter space D and L as follows. Where given a particular choice of shape hyperparameter, we need to also ensure that the score of the equivalent classes are equivalent. And while not emphasized in current literature, we can show that the prior under the choice, under the scenario of the BG score, is the analog of this more general class of DAG-Wishart prior with careful selection of shape hyperparameter. And so we use the method described by Geiger and Heckman in order to reconstruct compatible priors using the Cholesky parameterization for the space of the parameters in a graph. So here, by change of variable for every arbitrary DAG, for each of the node, we can then write down the corresponding prior, which you can see here as summarized, depends on the cardinality of the set of its parents. And one important point of this is one standard choice in literature for the hyperparameter lambda is a variant of the very popular G prior widely adopted in the context of variable selection. And so the choice of G in variable selection regulates the strength of prior belief in a variable selection problem, where larger G typically concentrates on the prior for parsimonious models with a few large coefficients, where we term that Linley paradox, and smaller G values tend to concentrate on the prior for saturated models with small coefficients. In the context of graphical model selection, usually when we adopt the default choice, it would tend to lead to a specific values of G that for example, in the denser graph context, would usually lead to higher false positive rate, because the choice of G is usually fixed and not depending on the data. And that gives motivation to adopt the fully Bayesian approach to handle the selection of G from the Bayesian, from the variable selection context into the graphical model selection problem by placing an appropriate class of models, an appropriate class of priors on the hyperparameter G. And one of our main theoretical contribution is to extend this result into the structured learning, the DAG structured learning problem. So in specific, we considered the following hierarchical model, where we also place a compatible prior on the DAG parameters D and L derived from the Cholesky decomposition of the covariance matrix. And we also place the Zellner-Seidel G prior on the hyperparameter G. For the priors on the DAG structure, we place an equivalent prior that is equivalent to placing a Bernoulli random variable on the edge indicator that indicates whether an edge is included in a graph with probability Q. And so a priori, we have the joint distribution for D and L, and we can then, because these priors are conjugate, we can then write the posterior distribution for D and L in closed form, where R is defined as follow. And the base vector between any two DAGs, G and G0, can also be written down tractably, where the base factor consistency between a grad G and G0 is consistent if the probability tends to 0 under the true graph model, which is G0. And in this context, the posterior ratio consistency has already been established for estimation for fixed G in a DAG context. And by utilizing the base factor upper bound in Cal, we can then generalize this to the posterior consistency for the compatible DAG-Wishart prior and the inverse gamma prior family on G. So in particular, we established that the posterior ratio between the marginal posterior probability assigned to a true graph, for the posterior ratio assigned to a non-true graph G to the posterior probability assigned to a true graph G0 tend to 0 in probability when the graph is not the underlying true graph G0. And we also adapt the sampling scheme that is derived from standard structure MCMC in order to accommodate both structural learning as well as parameter updates. So we first draw a graph proposal, G proposal from the appropriate proposal distribution, and conditioning on that, we then propose the Cholesky parameter from their respective conditional posterior distribution. And we accept this move with the standard Metropolis-Hastings probability defined as follow. We also have a within model move where we update the hyperparameter G by sampling their posterior, the Cholesky parameter from their conditional posterior distribution, and then draw G from its conditional posterior distribution using the samples from D and L. So to show the experimental results for the posterior distribution of G in comparison to the standard recommendation for the G value in model selection, we simulate two separate scenarios where the grand true DAG is empty, representing a scenario for sparser graph, and another scenario where the true graph is fully connected, representing a scenarios for denser graph. And we reflected the recommended choice for a fixed G based on Bayesian variable selection literature that usually recommend choosing G equal to the amount of sample data that you have, which indicates here that the update of G usually also agree with the recommendation choice based on the Bayesian variable selection literature. We also conduct more rigorous structured learning experiment in comparison to several baseline. In particular, we compare to order and partition MCMC, which are more advanced sampling methods in Bayesian structured learning, as well as no-tiers, which is a more optimization based on penalized likelihood. And we report the structural Hamming distance that measure the difference, the distance between the true and the estimated graph from our approach. And we also added in the null baseline where the graph predicts no edges. And so with the structural Hamming distance, the lower indicates better. And you can see here that our approach is quite competitive with respect to both more advanced sampling methods as well as optimized method. And so one interesting inference that you can get out of the structured learning is how to utilize all of the output in inferring causal effects from observational data. So DAGs are very useful in inferring as well as discover possible causal effects. And we can also utilize the results from our MCMC sampling scheme in order to derive causal effect estimation from observational data. And so here we let I be the set of intervention or target nodes. We can then write down the post-intervention distribution of the nodes x1 to xn given a particular intervention, which correspond to the following post-interventional distribution, where it depends on the covariance matrix given the intervention. And that means that we can reconstruct this covariance matrix using the samples of the Cholesky parameters as well as our DAG learning in order to reconstruct this. And based on existing literature on causal effect estimation from a joint intervention, we can then estimate the causal effects of a particular node xi on xb in a joint intervention is given by a function of the conditional on the covariance matrix. And so our line of current work focused on improving the current DAG proposal sampling procedure, as well as better quantify how accurately the Bayesian methods can recover the true graph posterior distribution and reflect uncertainty, an area that hasn't been well explored in literature. In addition, we would also identifying the best way of incorporating knowledge and interventional data into the learning process, as well as extending the modeling to potential misspecification in the likelihood model. And also that is the end of my presentation. Thank you very much for listening.
Thank you, Emma. Do you have any questions? I may start. So what is the dimension of the graph that you can handle with this method, like in terms of?
Yeah, so in the experimental result, we are actually focused on smaller graph, so up to 20 nodes so far. And the reason for that is usually most method when scaling up to more than 20 nodes, so from medium to larger networks, tend to have higher error rate. So we particularly focus on within a small network how to best reflect the accuracy of the sampling algorithms for small networks first before scaling it up. Yeah.
So you can build like a lot of small graphs. So.
Yeah, ideally we would like to, combining the result from smaller, when you break it down to smaller networks and combine it into a joint network, but that would require more research into how to combine that more effectively.
Yes.
Thanks for very nice talk. Can you go back to the posterior consistency result that you had?
Yes.
Yeah, so I wonder in case of specification for this result, would you still have that to concentrate around one particular graph? like with probability 1, like if that graph is not among the, so how can I phrase it? So here you're sort of assuming that the true graph is among the graphs you're searching in, right?
Yeah.
And this result tells you that you would concentrate with probability 1 around that graph.
Yeah.
So what if you have misspecification, then the true graph is not there, but will you still have that this probability goes to 1, but just on another graph?
So here we're assuming that the prior on G is, and the G choice is updated with the sampling scheme. So we that was one of the motivation to be more robust to misspecification on the choice of G hyperparameter. In a sense that we place a hyperparameter on the prior on G so that it would accurately reflect the amount of information with the data that we have. Yeah.
Yeah.
So my last question on the theory. I have a question about the presentation.
Oh yeah, sure.
SMC, right?
Yes.
How big the network is until SMC will break down in a few SMC?
Like when, well, usually structured MCMC, for example, because of the nature of the proposal, only change in one edge at a time is not very good for scaling up. That's why we have better, more advanced sampling algorithms like order or partition MCMC that make use of the topological order of the nodes in order to propose better proposal for the graphs. And that's one active line of work that we are currently improving on in order to utilize that topological node ordering in order to improve the proposal. But in general, it can potentially theoretically can scale up to like a large Bayesian network. Yes, so that.
And you use HNC or?
There's potential. That's actually a very interesting line of work recently that we could also reformalize the discrete nature of the graph space into a more continuous by assuming certain functions, loss functions, and in that sense, you can then have gradient and then apply optimize. That's right. Yeah.
Any other questions? Let's check online. Yeah. So no question online. So let's thank Emma again. So our next speaker is Anand Mathur. Yes. Who is from the School of Math and Stats of the University of New South Wales. Yep. Thank you, Anand.
Hi there. Firstly, I'd like to thank Clara and Kevin for putting together this event today and inviting me to speak. So I'll be talking about optimization methods for grouped variable selection. And what I'll try and do is present two new ideas which I've been working on in the past year or so with my supervisors, Sharat Moka and Zdravko Botev. So our core motivation is interpretable variable selection with groups of predictors. A clear example of this is in biology, where it's commonplace to come across very large genetic data sets for n individuals that might have a common complex trait. And this might be a genetically caused disease like heart disease or lung disease. And the data is stored as a sequence of genetic variants referred to as single nucleotide polymorphisms, or SNPs for short. And with the aid of domain knowledge expertise, these variations are grouped into specific genes. And then the question from a statistical perspective is, what are the genes which are most associated to this complex trait? So some notation to clearly delineate between the linear case and the group case. In linear regression, we have a matrix X, which has n rows and p columns, and we want to estimate a beta coefficient. In the group case, our matrix is actually pre-partitioned into J groups, capital J groups, and each of those groups will have a size of p subscript j. And then instead of trying to estimate beta, we're trying to estimate the vector theta j, which represents the coefficients belonging to the jth group. So in linear regression or in feature selection, the most common way to select features is to use constrained optimization. So constraining or regularizing our choice of parameters. And depending on what norm you use to constrain, you get different methods. So best subset selection is where you're constraining the number of non-zero elements in beta to be less than or equal to k. And for this, when it first came out, was thought of as the best way to perform feature selection, but over time, the statistics community, for the most part, ignored it because of its difficulty in being solved. It's a non-convex discrete problem. The Lasso problem is a convex relaxation of the best subset problem, and the constraint is now using the L1 norm, and there's some geometric intuition as to why using this norm actually enforces sparsity. But for the sake of brevity, I'll leave that out today. And then ridge regression, which uses the L2 norm, but actually doesn't induce sparsity, but it shrinks the regressors. Now, in the group setting, the two extensions of this is group best subset selection. So we're trying to minimize, we're now optimizing theta1 through to theta j. And we're minimizing our norm subject to the constraint that we have less than or equal to k active groups. And then group Lasso regression, we're now penalizing, instead of the individual magnitudes of beta, we're penalizing the norms of each coefficient vector. And in red, I've written down the penalized versions, which are in practice what we solve. And if you look at the Lasso, group Lasso penalty, this is quite interesting because it acts like Lasso penalty between groups, but within groups, it acts kind of like a ridge regression, and it shrinks our coefficients. So now focusing on the group Lasso, okay, the way this is solved for the past 15 years or so is using an algorithm called block coordinate descent, which means you iteratively go through each of the groups and minimize, say, theta1 with respect to everything else fixed. And then you move to the next group and you minimize with respect to that group, and then you cycle through all of the groups. And then you repeat this. You iteratively repeat this. Now, because this is a convex problem, it's actually easy to show that if you do this procedure, you'll actually obtain the global minimum at some point. So one issue with this method is that for very, very large data sets, this can take quite a long time to converge. So this is where our first contribution comes. So what we have here is an auxiliary method where we're going to define some new variables, gamma k, which is going to be in terms of our group coefficients and our penalty lambda, and a matrix G, which is a matrix that involves our group submatrices, xj, and our parameters gamma. And then we have a nice theorem that says, actually, we don't have to solve the Lasso objective. We have this equivalence between the Lasso KKT conditions and the auxiliary variables, which I just defined. So the first equation you can actually use to recover theta k using the gamma k's and g. And the second variable, the second equation, sorry, gives an equation which also needs to be satisfied. So in fact, you can come up with a new objective, which is only in terms of gamma and g, which satisfies equation 2, and then you can use equation 1 to recover the original group estimates. So that's what we're doing here. We're actually introducing a new optimization, which uses just G, which is in terms of G and gamma, and it turns out that this objective is a lot faster to minimize than the Lasso objective. And just as a demonstration on some simulated data, so we consistently observe an order of magnitude difference in outperformance of our method compared to the standard group Lasso. And just as a data point, the last data point has 15,000 groups, and the standard group Lasso algorithm takes 40 minutes or so, where ours just takes a minute. Okay, so now coming to the other version of group regularization, group best subset selection. Now, this is a lot harder problem to solve algorithmically because it's non-convex and it is discontinuous. So for the past 20 years or so, this has purely been dealt with people interested in combinatorial and discrete optimization. So our second contribution here is going to try and use continuous optimization to try and solve the best subset selection problem. So in the exact method, you can think of that one way for selecting the subset you're going to choose is by representing it with a binary vector. And then once you select your groups, you can just evaluate the normal least squares estimate. And in the naive brute force method, you try and traverse all binary vectors with k1s in them, and then evaluate the loss and find the minimum. So the continuous method is, instead of trying to traverse these binary vectors, we're going to introduce a vector t, which lives in the j-dimensional hypercube, and we're going to multiply each of the groups by elements of this vector t, right? And then we're going to define this new estimate theta tilde, which is now in terms of this xt matrix, which is all the groups multiplied by t. And the nice thing about this theta tilde now is that it's defined for all these interior points. It's defined for all t in the cube, and it agrees with the exact estimate at the corner points. So to see how this works in practice, this is a two-dimensional case. Sorry, a case where we have two groups. And on the top left, we have at the corners a representation of the exact loss evaluated at the binary vectors. And obviously, when you're including all the groups, you'll have the smallest loss. So the continuous method now allows you to place like a continuous blanket of all of these exact values. And instead of trying to discretely or combinatorially traverse all of the corner points, we can implement the gradient method and start at an interior point and then move towards one of the corner points. Now, in this case, in the top right, we're always going to, if we place a continuous blanket on all the values, we'll always approach the case where we're including all the groups, obviously. So we need to penalize t. So that's what we do in our method. We penalize, we're using an L1 norm of t, so that the corners with more groups in them, or more ones in them, will be penalized. Right, so this means now that we'll approach a sparse corner, which will be hopefully one of the better choices of the subsets. And obviously, if you make this penalty large enough, eventually you'll approach the case where you're not including any groups. So like in Lasso and Ridge, you'll have to play around with the lambda penalty to induce the amount of sparsity you want. So here's an example where so in a high dimensional case, you can start your initial value at like the midpoint of the high dimensional cube. And because the loss function is defined now for all t and it's continuous, you can actually evaluate gradients quite nicely. So you'd start you'd start at the midpoint, and you'd perform something like gradient descent, and some of the t components will go to 1 and some will go to 0. And the ones that go to 1 correspond to groups that are suggested you should include in your model. And there's also a nice stochastic gradient version where this is a lot cheaper to implement, and you can come up with unbiased estimates of the gradient using less computations. So in terms of what else I can do, so actually there's been some really interesting research lately that shows that the L0, using the L0, the best subset method, actually may be disadvantageous in cases where you have lots of noise. And actually one of the authors is from University of Sydney, and they suggest that you should combine the L0 penalty with the L2 penalty. Because you can think of it, the L0 penalty will give you a choice of subset, will give you a discrete choice, but then it won't regularize the estimated values. So that can lead to overfitting when in the case you have high noise. So what I'm now trying to work on is including more than one penalty in this continuous optimization algorithm, L0 plus something like L2. And this will, initial experiments suggest that this actually works better, not only for model selection, but also for prediction. And the relevant to the Lassell method, the one thing I can focus on is some theoretical results showing that the auxiliary method that I introduced exhibits an improved rate of convergence. We have lots of simulations and experiments, but what I want is some clear theoretical understanding of perhaps in what cases, what does my data have to look like to see the best gain for our auxiliary method. And rates of convergence, they always seem harder than they initially look. So we'll see how we go. Thank you.
Do you have any questions?
You were just mentioning the combination of L's for penalty. So have you thought of elastic net version of which is the L1 and L2?
Yeah, so the that's L1 and L2. What recent research suggests is actually you want the L0 part as well. So that's more aligning with choosing a subset rather than continuous penalization. And then if you combine the L0 with L2, you get the added benefit of regularizing your coefficients. So I know elastic net, I haven't actually seen elastic net used in the group setting, but definitely this L0 plus L2 setting I've seen, and which I'm now trying to implement in my new algorithm.
Two things come to mind. Is it possible that that continuous optimization is optimized not on a corner?
Yeah, so this here was a nice case where everything goes to 0 and 1. I've seen examples where you'll have some of the trajectories going to 0, but some of them not necessarily going to 1, but going to some non-zero value. So there you can still infer feature selection by saying the ones that go to 0, I'm going to exclude, they're not important. And a lot of this has to do with the continuous function we defined. Here, this is a non-convex function. And this parameter delta here, which we've left it up to the user to choose, affects how this graph may look like. So depending on the properties of this continuous map, you may end up not exactly approaching a corner. Yeah, yeah.
One of the big questions was the penalty you used multiplying the t vector.
You mean here?
Correspondence in the discrete. Does that multiply?
Yeah, I mean, you can, the issue here, so normally the group best subset is, you constrain so you can represent, instead of theta j here, you can represent this by a binary vector S, where S, the entries in S would correspond to each group. And then you constrain that to be less than or equal to K. And now we're relaxing that to be T, which is now continuous. And then you get your Lagrange penalty. But none of these are equivalent because this is all non-convex stuff. So you can't say that there's an equivalent between the lambda penalty and the subset size.
Maybe I missed it, but you kind of say, well, people don't do best subset because it's very hard, and then you jump to doing best subsets in the group.
Yeah, so yeah.
About best subsets.
So I should say it was hard up until 3 or 4 years ago. And then famous work came out introducing a mixed integer optimization framework for solving best subset. This is kind of like the next iteration. So yeah, I should say that this, my supervisor has recently published work applying this continuous method to the just normal feature selection case, and I can refer that to you if you'd like.
Okay, let's thank, no, there is nothing online. So let's thank Anna again.
Our next speaker is Annabelle Webb.
Who comes from the School of Mathematical and Physical Sciences of Macquarie University. Thank you, Annabelle.
Thanks so much. Okay, so thanks very much. Today I'm going to be talking about a penalized likelihood estimation method for Cox models with time-varying covariates for partly interval censored survival data. And this is joint work with one of my supervisors, John Ma. Okay, so our goal here is to model a time to event outcome using a semi-parametric Cox model. That includes a time-varying covariate. So we have this model where we have the hazard function or the instantaneous risk, the baseline hazard function HOT, which is non-parametric and is known to be smooth and non-negative, and then the regression part, which here will include time-fixed covariates X and time-varying covariates Zi of T, and the two regression parameters beta and gamma. In this context, we're considering time-varying covariates which may be discrete. So for instance, they may represent moving between different treatment groups at different times, or they could be continuous. So for instance, repeated measurements of some biomarker or other continuous variable. But in practice, we have observations of the time-varying covariates at a series of discrete time points. So for individual I, we would have a series of TIAs at which we're observing the value of the time-varying covariate. And in this work, we're assuming that the time-varying covariate is observed without any measurement error. So unlike, for instance, a joint modeling approach. So if we have a time-to-event data set that only contains exactly observed event times and right censoring times, where the event hasn't occurred by the end of the follow-up, we can estimate the regression parameters in this extended Cox model using the typical partial likelihood. So we're still able to define our risk set and estimate our regression parameters using this partial likelihood, which leaves the non-parametric baseline hazard function arbitrary. However, we're interested now in extending this to a partly interval censored setting. So this type of partly interval censoring can arise from a study design sort of represented by this schema here. So for instance, if we've got a study design where the participants are checked at repeated appointments. We might have right censoring where there's still no event. We might have interval censoring where the event is occurring between checkups, so we don't observe it exactly. We might have left censoring, which is just a special case of interval censoring. Of course, we might happen to also have exactly observed event times. And if we have some generic combination of these different censoring types, we would call that partly interval censoring. And when we have partly interval censoring, we're no longer able to use the partial likelihood to estimate the regression parameters because we can't express a likelihood where the baseline hazard function is arbitrary. So to address this problem, we are building on existing maximum penalized likelihood methods for partly interval censored survival data. And we use a spline approximation to the baseline hazard function. So specifically this linear combination of some non-negative basis functions psi and the spline coefficients theta. And the selection of a non-negative basis function here means we just have to restrict all of the theta to be non-negative so that we have a non-negative approximation to the baseline hazard. Correspondingly, if we're using non-negative basis functions, we can express the cumulative baseline hazard in terms of the same spline coefficients theta and the cumulative basis functions. So in this work, for instance, we've primarily used M splines for the baseline hazard. So correspondingly, these would be I splines. And then we can define our baseline, our cumulative hazard function in terms of this term here, HOI star, which just involves all of the time varying, the time dependent parts of the model of this integral. So to simplify computation in our approach, we treat the time varying covariates as, we assume that we can treat the time varying covariates as discrete stepwise functions. So essentially assuming that any time varying covariate ZIT remains constant between each of the observation times for each individual. Although we don't necessarily assume that those observation times are the same for each individual in any sample. Since now we have discrete ZIT, we can obviously simplify the expression for the psi UIT with the integral into a summation. So we're fitting this model to survival data with partly interval censoring. So I'll just introduce some notation. So when we have partly interval censoring, we are assuming that we're observing this random vector Ti made up of TIL and TIR. And the nature of this vector tells us what type of censoring we might have. So for instance, if we have TIL is equal to 0, that would be left censoring. With TIR equal to infinity, that would be right censoring, and so on. But in general, we can just use some indicator variables to denote the different types of censoring. And in particular, when we're considering this vector or the interval within which we're observing a time to event, we don't necessarily require that these TILs or TIRs are equal to any TIA. So essentially, we're allowing the process that might be monitoring the event status and the process monitoring the time varying covariate to be independent of each other. Okay, so our goal now is to estimate the three parameters, beta, gamma, and theta, subject to theta greater than or equal to 0. And now instead of a partial likelihood, we can express the log likelihood like so, where we have a term each for the contribution of the exact event times, right censored times, left censored times, and interval censored times. This log likelihood is penalized, giving this phi of eta. So we have the penalty term lambda times, we have the penalty function j of theta and the smoothing parameter lambda. In our approach, we're adopting a quadratic roughness penalty given by the L2 norm of the baseline hazard function, which given our approximation to the baseline hazard function, we can actually just re-express in terms of theta, so the spline coefficients and the penalty matrix R. So our maximum penalized likelihood estimates of beta, gamma, and theta are given by maximizing this penalized likelihood subject to theta greater than or equal to 0. So this is a constrained optimization problem that we solve using what we call the Newton MI algorithm, so multiplicative iterative. In practice, essentially at each iteration, beta and gamma are updated using a typical Newton step, and theta is updated using a multiplicative iterative step to ensure that it's non-negative. In our method, we also adopt an approach for choosing automatically selecting the optimal value of the smoothing parameter, lambda. So we're borrowing from essentially a restricted maximum likelihood approach. So if we can see here, if we relate our spline coefficients theta to a normal prior with a covariance matrix related to this penalty, we can re-express our penalized likelihood in terms of a log posterior, where we have our likelihood of the beta, gamma, and theta, and then this term corresponding to our penalty term. We can then use this to find the marginal likelihood with respect to sigma squared, which is just a transformation of the smoothing parameter, and then maximize this or find a solution to this. So our approximate solution for selecting sigma squared here is given here. So in practice, after the Newton MI algorithm would converge, we would update the smoothing parameter using this solution, and then iterate back between the two sort of stages of the algorithm until both have stabilized. Okay. We're also able to derive asymptotic normality results to derive a covariance matrix for the three parameters, so beta, gamma, and theta. So we have this sandwich formula involving this term A, which is given here. So there's two important elements of this sandwich formula. So firstly, it allows us to incorporate the penalty into the estimation of the covariance. And secondly, it includes this vector U, and this is used to deal with any active constraints in our estimation of theta. So essentially at convergence, we may have some theta that are very, very close to 0. So we can use this U matrix, U vector to pad the covariance matrix. In terms of the practical use of these results, what this means is that we're able to derive asymptotic covariance results for the spline coefficients, and then use the delta method to derive asymptotic standard error results for survival quantities, such as the survival function. So lastly, I'd like to show an illustration of the method using a data set on breast cancer recurrence. So we investigated time to breast cancer recurrence using this data set from Duke in the US. So this contained data on 902 breast cancer patients collected from 2000 to 2014. And in this data set, all of the individuals either had a right-censored time to recurrence, so they didn't experience recurrence by the end of the study, or they were left-censored or interval-censored. And this data set contained a large number of variables, but for the purpose of selecting illustrating our method, we just selected a small subset. So we had the time-fixed covariates age at diagnosis, spread to the lymph nodes at diagnosis, cancer subtypes, specifically if it was triple negative or a different subtype, and then the staging in terms of the size and location. And then we had a time-varying covariate indicating whether or not a patient had undergone one of two possible surgical interventions, so either breast conservation surgery, BCS, or mastectomy. Okay, so here I'm showing results from fitting the model with the variables that we selected. So in the first set of results, these are from the extended Cox model that I've been discussing. And then on the right, from a typical Cox model, accounting for interval censoring, so fitted using the survival MPL package, which allows for interval censored data and uses a similar spline approximation, but now sort of ignoring the time varying nature of the surgical intervention, so just setting it to the value at the end of follow-up. And we can see that the time fixed covariates have relatively similar results in terms of their estimates of the regression parameters, but ignoring the time varying nature of the surgery variables means we're actually seemingly underestimating the effect of surgery on the risk of recurrence in the typical Cox model compared to the extended Cox model where they're treated as time varying covariates. Okay, so as I mentioned, we're able to derive asymptotic standard error estimates for survival quantities like the survival function and the cumulative hazard function. So here we have the estimates using the spline approximation with the pointwise 95% confidence intervals for the baseline survival and the baseline hazard. And we're also able to plot estimated survival probabilities across time for different combinations of covariates. So for example, we have holding all of the time fixed covariates constant and just changing what type of surgery a patient had. So having no surgery in the gray and then either BCS or mastectomy. And we can see the significant difference in the risk of probability, in the probability of recurrence across time. So to conclude, this MPL method for fitting an extended Cox model allows for flexibility in terms of the censoring and complexities in terms of study design, as well as flexibility in terms of the monitoring process of both the event and the time varying covariate. We're able to compute survival quantities of interest, such as predicted survival functions, along with pointwise confidence intervals. We plan on updating the survival MPL package, which is currently on CRAN, to include this method in the near future. And in the future, we're also planning on extending this to joint modeling to account for measurement error in the time varying covariate, and also to incorporate time varying covariates into existing MPL methods for partly interval censored survival data. There's a small number of references. Thank you.
Thank you, Annabelle. Do you have any questions? Yeah.
Thanks very much, Annabelle. That was really interesting. Toward the end there, you had the comparison between what happens when you take into account time varying and you get smaller standard error.
Yes.
So with those confidence blocks that you did afterwards, I'm curious, with the separation between those staying if you use the old existing methods, or do they blur together?
That's a good question. I haven't actually looked, but I imagine they would blur together. Yeah, because obviously, yeah, it would make a big difference.
Okay, right.
Thanks. Yeah.
Thanks for an interesting talk. I wonder, you were using a spline and something to model the hazard. And so I wonder how sensitive are the model parameter estimates to how you, for example, choose the knots and where to place the knots and stuff in that non-parametric?
Yeah, so we've found it should be relatively non-sensitive to the selection of the number of knots with the penalty function that should sort of regularize that approximation and mean that the beta and gamma estimates aren't massively affected by the choice of knots. We're still planning on experimenting. Obviously here we've only used an L2 norm. We're planning on experimenting with different penalty functions and seeing if one is particular, one gives less sensitivity to the number of knots versus another. In general, it seems relatively stable.
Are you optimizing everything jointly, or is it like holding one fixed and updating the model parameters?
We're optimizing beta, gamma, and theta jointly, and then updating the smoothing parameter, holding the smoothing parameter fixed, and then updating beta, gamma, and theta jointly. Yeah.
Okay, so let's thank Annabelle again.
I have two versions is okay. So one is paper color.
Just in case.
Okay, great. So our next speaker is Kieran Lucan. Yeah, okay. Who is from supported by the School of Computer Science of Western Sydney University, and that's 61, right? Yes, correct. Thank you. Let me open it. Thank you very much.
Move those out of the way. Hey, so welcome everyone. Thank you for coming along and paying attention. My name's Kieran. Really long title. Basically what I'm trying to do is work out how far away other galaxies are. Okay, is what the gist of all that says. So all of this is prompted by, we've got a whole bunch of new radio telescopes coming along. Partly over here, we've got a big telescope over in Western Australia called the ASCAP. About $200 million worth of government money going into that. So we really want to make sure we optimize everything we can out of that. One of the things that we'll do is a survey of the entire southern sky. So everything we can see with this telescope. Okay, it is producing some absolutely fantastic images, stuff that we haven't ever seen before. So this, for example, is what we're calling an odd radio circle, or an AUC. Something found a couple of years ago in one of our first pilot surveys. Okay, so we're getting some really cool stuff coming out of it. One thing we can't get out of it though is the distance to anything. So one of the things we can't do, we can't look at any of these point sources and go, is this near? Is this something like an asteroid or a comet or something, or a star or something like that? Or is it a galaxy on the edge of the universe? Okay, so that's one of the downsides of having something like this. So one of the ways, or one of the easiest ways to work out that distance is just using parallax. So we have our motion around the sun. We can measure where the position of a particular object is on the sky 6 months apart. The difference between that position is our angle. We can use trigonometry to work out how far away that thing is. Really good for really close things. Really far things, they don't move. So I mean, that is one of the ways that we can work out stars. If they're moving in 6 months, chances are they're nearby. Okay, so it only works for nearby stuff. To go further, we need to look at its spectrum. Okay, so this is one of the best ways to work out its redshift or its distance, is looking at its spectrum and seeing how the acceleration of the universe, the expansion of the universe has stretched its spectrum. So we can grab spectrums of, or spectra of multiple objects. Generally, we're still only looking at hundreds or thousands at a time. So it is very time consuming. We can look at these spectra, we can point out these features, work out what those elements are, compare them to where they should be. And that difference will generally result in a red-shifted spectrum, a spectrum that is shifted and stretched towards the red end of the spectrum. Okay, hence redshift. So once we have how much that's shifted, if we take that into account with some kind of cosmological model, we can then work out how far away this thing is. And by the same token, we can also work out how old it is. So the redshift gives us some useful information. Unfortunately, as I said, we can only do these things a few hundred to a few thousand at a time. Okay, the alternative is we can measure them photometrically. So we can grab a whole bunch of telescopes, we can point them at a large patch of sky, have them take a picture through a particular filter. From that, we get brightnesses at different peaks. And if we have enough of these photometric data points, we can get something that looks kind of like a spectrum. And again, we can work out its redshift based on this. Really, really accurate, but again, to get the number of telescopes looking at these particular objects in these quantities is still very tricky. For the most part, we have about 8 data points. So we have spectrum that look like this, that we're trying to work out what the redshift is. So the top one, fairly easy, because we have at least one bump. We have a bump and we go up some more. So we do have a little bit of structure there that we can start to play with. Okay, the downside to all of this sort of stuff is radio telescopes don't pick up many of these objects. For our radio telescopes, a lot of the things that we're seeing with those radio telescopes are the emission out around black holes. The emission out of black holes looks much more similar to this. So when we've got new surveys coming through with in the radio spectrum, we're looking at a whole bunch of these objects. Most of them will have a spectral energy distribution, so we're not looking at a full spectrum at this point. We're just looking at how is this energy distributed across a much wider band. They're all looking very similar to this. So this is looking at, so we've got the visible spectrum just here. This is going all the way from blue into the infrared. Okay, and radio is off to the right side, really far away. Okay, so as I mentioned, really hard to do with something with such a small number of data points for each galaxy. Harder when we're looking at radio selected sources, which again is a problem, because when we're starting to look at how many radio sources we know of, with a few of these telescopes, we are getting up into the tens of millions of sources. Still not as many as we know of other sources. So for example, optically and infrared, we're looking at billions of sources, but we're still looking at a large number of sources that we just don't know how far away they are, or we can't get accurate estimates. So coming into where I'm actually starting to do stuff. So a couple of years ago, there was the EMU pilot survey, short for the Evolutionary Map of the Universe. It was a pilot survey for the main all-sky survey. It's 270 square degrees. This is the size of the moon in comparison. So it is a very large patch of the sky. When it was done in 2021, it was the largest, deepest survey that we'd had so far. We have all-sky surveys, but they haven't gone as deep. We have small surveys that go deeper, but nowhere near as big. So this is one of the first ones in the middle region. Just for a little bit of context, entire southern sky reachable from some of our telescopes is about 30,000 square degrees. So it's, again, a very small subset of what we will get. From this, we had about 200,000 objects detected. I say objects in quotation marks because they are the things that are coming up in our telescope. They might be, for example, if we have a look at this first object, our telescope might pick up this part as one object, this part as one object, this part as one object, this part as one object. So just because there are objects detected does not mean there are galaxies detected or sources that are detected. So we've got around 200,000 objects detected. Of that, we have about 100,000 sources we're trying to work out how far away they are. So just to summarize all of that, radio galaxies are more difficult than normal galaxies, normal being selected by optical telescopes. Given that we have so many coming through, what's the best way to estimate their redshift? Okay. And like most problems the world faces, at some point, people have thrown machine learning at it. And I would imagine it would be the same in most fields. Most people have grabbed an off-the-shelf piece of software and gone, don't change anything, throw that software at it, get results, report results, move on. In astronomy, that happens a lot. We get a whole bunch of neural networks that are used just off the shelf, throw results, get results, publish them. One of the things that we were trying to do was work out, given we have 8 data points for each galaxy, do we actually need something that complex? Hence why we're looking at the first 2, K nearest neighbors, incredibly dumb, incredibly old. Again, like most things, if you're actually optimizing the thing, it performs better. Random forests, not so good for this use case, don't do it. ANNZ is a piece of software written for this. It is an ensemble method that's going to combine generally hundreds of randomly initialized neural networks and boosted decision trees and stuff like that, combine them all into a single value to give you a redshift. Pretty big sort of effort to go into for that. And then GPZ is a way of using Gaussian process regression to handle this as well. So some complex or some more complex algorithms, some more simple algorithms. Complex does not always equal good though, and I'll show why. One of the other things astronomers really want is they don't want standard error metrics. The average error is not necessarily the best error. what would be more interesting is we can get these low redshift points, we can work out their redshift reasonably easily. Just because we can get those ones, how does it handle the ones up? How do we handle the ones further away? If we're going to optimize our model for the best overall accuracy or best overall error, chances are we're going to be ignoring the few data points at the high redshift, the ones that are actually kind of interesting, and just making sure we get the ones at the low redshift, getting those right. Astronomers don't like that. They want to know what these high-end ones are. So we need to talk about some other error metric. In this case, we're looking at catastrophic error, catastrophic outlier rate. The idea behind this is we're trying to work out, we have our 0.15 error, plus or minus 0.15 that we're accepting of, but we're going to scale that with redshift. So the higher we go in redshift, the more accepting we are of error. So you'll see a few plots like this. You'll have the teal dashed line through the center. That would be a perfect prediction. That is ideal. Or there's the blue dashed lines, which are representative of the catastrophic outlier rate. So we want them ideally along the teal line, if not within those blue bounds. So looking at our results, as I said, I'm not showing random forest because they kind of suck. K nearest neighbors, ANNZ, the neural network, and GPZ, the Gaussian process. We find that K nearest neighbors is performing the best. We have the lowest outlier rate. Okay, neural networks, Gaussian processes, both do reasonable, but they are still significantly worse than the 7% outlier rate we've got. This does sort of ignore, looking at results this way does sort of ignore some of the benefits of the other algorithms. So KNN does not naturally provide errors, does not naturally provide confidence intervals. It also doesn't naturally provide any kind of probability distribution functions, which would also be useful. And it doesn't extrapolate beyond the training data. Not suggesting that others do well, but anything is better than nothing when you don't have anything representative in your training data. We can try to work out what our more certain predictions are. So if we're looking at our confident predictions, K nearest neighbors and ANNZ, the neural network algorithm, are both sort of hacked together confidence levels. If we're just looking at those that are confident, again, K nearest neighbors comes out the best. Again, still has some problems, but the Gaussian process and the neural networks come out to be roughly equal. Either way, we're still getting about 3% outlier rates, which is better than what most people are getting. So all of this is good. We've done all of this with training data where we know our redshifts. One thing we don't know is the redshifts of the pilot survey. So we don't actually have any ground truth to compare to there. Alternatively, we can start comparing our algorithms against each other. So in both of these plots, we can see we've got the Gaussian process on the x-axis, K nearest neighbors on the top, ANNZ on the bottom, and we can see that there is a whole lot of scatter if we're just looking at every prediction within those 100,000 sources we've got. So we can then restrict those just to those confident sources, the same way we were looking at before. Given that GPZ provides the best levels of uncertainties because it comes out naturally from a Gaussian process, I'm just showing the sources that are confident according to the Gaussian process regression. And we get much more acceptable estimates. Our algorithms are much more in line with each other. Okay, so hopefully that means that we've got more of a trustworthy sample. Still trying to work out exactly what we mean by trustworthy, but we're trying to get there. But based on that, they look different anyway. Based on that, we can show some histograms. So exactly what are the redshift distributions of these algorithms? They all peak at roughly the same. They're all peaking between, almost done. Peaking between 0 and 1. We do have a little bit of a bump with the neural network that could just be part of one of the other distributions, but we do have some predictions coming through. That was it for me. Thank you for listening. Thank you for hosting the event, and thank you for CDMS at Western Sydney for nominating me. Any questions?
Do you have any questions? Yes, sorry.
Thank you. Oh, Karen. Have you checked to see if there's any clustering in RA and DEC URL?
Yes and no. Preliminary, clustering in RA and DEC is problematic for some of the algorithms. Some of them will just overcompensate. Some of them will, sorry, not overcompensate. Some of them will overfit on those features. So yes, in some cases there are, but it's hard to work out exactly when and how to train those. Because that would be really cool, because if we can then start to look at cosmic web and can we actually identify that in our large scale surveys.
Yeah. So good that we're going to compare the GB to the other members.
Yep.
You know, and there's one previous.
Yep.
There seems to be a fairly sort of natural relationship between the neural networks and the GB, but there's always that link with the neural networks. You know, that bit that's going up. So do you have any intuition around what is causing that? Is that, you've got any intuition about what it is about those?
That is purely training set based. So that is k-nearest neighbors going, we have a small number of sources that we can pick from. So we're just going to take the average of the 6 that match us. Whereas GPZ and ANNZ are both attempting to model the entire redshift range in our training set. So it's just easier for KNN to pick out those. Yeah. So, I mean, that does bring up the next issue, in that how do you actually make sure that our training sets are representative enough? And that's a big thing. Astronomy is messy.
I actually had a question. Sometimes I work with models where you have like source identification and then like a focus on R,
Yep.
like a thank leader problem. So one of the possibilities is actually to use a model where the location or the distance of the source is unknown, and you can estimate that. So are you aware of, like, instead of using a machine learning technique, like using a statistical model, and is it doable, or is much like there are disadvantages?
Yes, and this is where photometry of this level is particularly good. So one of the main ways that people have traditionally done photometric redshift, so instead of directly measuring it, they grab photometry like this. They will create models of all the possible galaxy types. They'll shift them to all possible redshifts, and they'll just pick out which one matches the spectrum best. So that is very common. That struggles very much with these. So that, for a couple of reasons. One is it is just that there's no features here, that there's nothing for it to actually pick up on to be able to shift. But on top of that, we don't actually have good templates for radio galaxies at this point, because we don't have so many as everything else. It's being worked on, but not yet. Cool. Yeah.
Just for you were saying a wave of things that are close, you see their movement.
Yep.
Given time, is there anything that changes in the spectrum?
So,
because for the close thing, you see the position, and that helps, right?
Yep.
For the parting, will the spectra actually have a certain state that you would expect to see?
Yes.
Or not?
Yep, that's all of this stuff. That is the redshift. Yeah. So that's basically just as the universe is expanding and accelerating its expansion, that spectrum is shifting. It's taking longer for those electrons to get to us.
No, in my visual thing, it'd be bigger, maybe it's bigger or it's closer, but then regardless of spectra, it will be regardless of the path or how far it is.
That will all come into play. So the mass and things you can work out based on redshift and based on brightness. If you know both of them, you can then work out how big the thing is physically, and therefore if it's that big physically and that bright, how dense is it and all that sort of things. Yeah.
Okay, so I'll just double check if there is anything in mind. No, like if there was questions.
Oh, sorry.
But thank you, Kieran, again. Okay. Last speaker is online. Yes. Is Morshadur Rahman. Hello. Can you try to speak?
Can you hear me?
Yes, we can hear you.
Yeah.
Perfect. So,
share screen myself.
yeah, I think so. Can you share your screen with the slide?
Give me a moment.
So we can share it as well, but maybe it's easier if you share it. Yes, we can see it. Okay.
Yes.
Perfect. Yes. So I won't be able to give you the 5 minutes and but I think you can get it. So Morshadur Rahman is supported by the School of Public Health of UTS, but is now currently in Tasmania. So you can join us online. But thank you, Morshadur. And I'll come back when you finish and repeat the question that I get from the audience.
Yeah,
thank you.
Thank you. Thank you, everyone. My name is MD Morshadur Rahman. So I'm a PhD student at the School of Public Health at UTS. So my today's topic is regular blood donation and the risk of mortality, minimizing the impact of the healthy donor effect. So at first I want to talk about some background behind this research topic. So most of the previous donor health studies that continuously demonstrated the beneficial effect of blood donation. So blood donors experienced lower mortality, lower cancer, and lower cardiovascular disease incidence. So these results might happen as blood donors are mostly selected healthier subset of the general population. And to be eligible for both starting blood donation and or continue blood donation, people must meet certain health and lifestyle criteria. So this better health status of blood donation, it is actually known as healthy donor effect. And it's a combination of selection bias and confounding effect. And healthy donor effect may lead to false beneficial effect of blood donation. And most of the previous studies that could not actually rule out the effect of the residual healthy donor effect. And adjusting the healthy donor effect is methodologically challenging if we compare between donors versus non-donors. So in this study, we try to investigate the association of blood donation and all-cause mortality after adjusting the healthy donor effect by applying target trial emulation and exposure window technique. So I also want to talk more about healthy donor effect to give some more background. So healthy donor effect is a methodological problem in donor health research, and it arises mainly combination of 3 types of biases. So the first one, if you can see, it's written as HRE. So it is a healthy registration effect. So healthy people are more capable and interested in becoming blood donors. When a person wants to donate blood, they must pass a number of health and lifestyle criteria. And as a result, when compared to non-donor, blood donors are healthier, which is called healthy registration effect. And second one is less healthy donors usually stop donating more sooner than the healthier person. So thus it is more likely that active donors who regularly donate are on average healthier than the inactive or lapsed donors. So this is known as healthy donor survivor effect, or HDSC. And then the last one is the healthy donor carrier effect, or HDC, which arises in analysis that compare health outcomes within the active donor population. And since blood donors face repeated medical checkups throughout their donation career, donors who donate at their high frequency are also healthier than the low frequency donors. So because of this bias, it's very challenging in donor health studies to make inferences whether the health outcomes measured occur due to the effect of blood donation or due to the healthy donor effect. And therefore, acknowledging and adequately adjusting in healthy donor effect in donor health research is very crucial. So now I want to talk about the first method I used here. It's called target trial emulation technique. So sometimes it's actually quite impossible to conduct a randomized controlled trial because of the cost, feasibility, ethical issue, and time. And in those scenarios, one can attempt to emulate a target trial through the analysis of the observational databases. And if the trial emulation is successful, the analysis of the observational data can yield same effect estimates as the target trial would have yielded. To emulate the target trial, we basically need large or big amount of data. So in this study, what I did, I tried to emulate a target trial of blood donors by using the Sachs Institute's 45 and up study data, which is linked to other administrative health databases of New South Wales. And also we have Australian Red Cross Live Blood donor dataset. So the Sachs Institute's 45 and up study is one of the largest prospective health-related cohort study that's ever conducted in New South Wales. And it consists of almost 267,000 residents aged over 45 and up and recruited to the study to provide their detailed information of health, lifestyle, and also their demographic criteria. So to emulate the target trial by these observational databases, at first we created one specific trial and we named it July 2006 trial. So the people who are eligible to be included in this trial, they are participants who were enrolled in the 45 and up study before July 2006. So 45 and up study, it was the recruitment was done by between 2006 and 2009. So we took here people who were recruited before July 2006 and who were less than 70 years old in July 2006 and who did not donate any blood 2 years prior July 2006. So we used that as a kind of a grace period. And also the people who didn't have any chronic disease or cardiovascular or any infectious disease or cancer before that month. And also we divided to treatment and follow-up. So donors who donated blood, we regarded them as blood donor, and who did not donate, non-donor, and follow-up time. So until an individual die or until 5 years after follow-up is started. We also did several sensitivity analysis by varying follow-up time and exposure, follow-up time and trial period. I'll discuss them later. So emulating one trial basically gave us a very small number of people and a small number of events. So what we did, we created a sequence of trial. So from July 2006 to June 2011, for every month, we applied the same eligibility criteria. And it actually gave us 60 non-randomized trial, and the follow-up time and everything was same, like dividing the people into blood donor and non-donor categories. And this figure actually give us the actual scenario of how many people we actually got from the overall trial. So we had 5,837 donors and more than 257,000 non-donors, and we get like 44 cases from donor group and 3,381 cases from non-donor group. And we used several confounding factors because from 45 and up study data, we got them from here, 45 and up study data, and also from other administrative health databases. And in the analysis, we use intention to treat hazard ratio, and we calculated a standardized survival curve. So what we did, intention to treat hazard ratio, we actually approximated it by pooled logistic regression model. You can see the equation here. And also the standardized survival curve. So it's just basically same, but what we did, since hazard ratio can vary over time, so we put an indicator of product terms between treatment indicator and follow-up, so that the hazard can vary over time. And from there, we calculated the standardized survival curve. So in the results section, you can see how many people we get and how many unique cases. And if we see that unadjusted, age and sex adjusted, and adjusted for all covariates. So if we adjust all covariates, then it actually gives null values, the hazard ratio. And that means there is kind of no association between blood donation and all-cause mortality. And also, standardized survival curve text also gives, because it's like 0.99, so it's very small difference actually. Okay, so now the method 2. So in the previous method, we basically compared between donor and non-donor. And by using this method, it's called a 5-year exposure period or exposure window, we can compare between regular high frequency and low frequency donors. So basically, exposure window technique is used to identify active donors who do not develop outcomes within 5-year window. And this process removes the healthy donor registration and healthy donor survivor effect. So the exposure window basically refers to the duration in which the donor is required to donate blood actively while meeting other criteria for eligibility. So in this study, this exposure window spans 3 years before the recruitment into the 45 and up study, and 2 years after that. And to qualify for inclusion in this study, donors must have made at least one whole blood donation during this full 5 years period. During this first and last years of this 5 years period. And therefore, the study population consists of individuals who had an active donation career of 5 years during the exposure window period. And we also followed them for 7 years after they completed the exposure window. And we divide the donor into 2 groups. So high frequency donors, so at least 2 donation in each year of the exposure group. That means each year, that means the 5 years, and every year they donated at least 2. And low frequency, less than 2 donation in each year. And also, in the analysis, we used inverse probability weighting and also targeted minimum loss-based estimator. So in the results section, we can see inverse probability weighted estimates, risk ratio 0.98, and also targeted minimum loss-based estimator, also very close, very similar. And we also used time varying targeted minimum loss-based estimator. That means I used some of the time varying variables. That means number of GP visits or number of referrals or comorbidity indexes measured in each year. And time varying TMLE and also that TMLE model that actually also used some ensemble algorithms, machine learning algorithms. So here we can see the unweighted and inverse probability weighted survival curves for 7 years of follow-up period. And it's very clear that there is basically not much difference for low and high frequency donors. Like the results are quite similar what we got from the target value emulation. So the key findings from this study. So we applied 2 of the methods, and the findings are basically different because in the target value emulation that actually compared between donor and non-donor. And in the exposure window technique, it compared between high frequency donors and low frequency donors. And in both results, we could not find any significant association with mortality. And in terms of strength, that means like how actually we adjusted the healthy donor effect. So we continuously applied eligibility criteria for all the trials, which could reduce the healthy donor registration effect. And also we adjusted trial-specific baseline confounding factors that also can reduce the healthy donor registration and registration effect. And in exposure window technique, basically we compared within donor population, and also we separated the exposure period and follow-up period, which basically can reduce the healthy donor survivor and healthy donor carrier effect. There are also some limitations. So this is the 45 and up study data. So the people are basically older Australian people. And if we compare with some other previous studies, our sample size was a bit smaller than some other studies. And the donor participants were largely non-adherent to initial donation status. So that's why we basically did not. So this limitation is for target trial technique. That's why we could not compare the prevalent donor versus non-donor or continuous donor versus non-donor effect, which also is called per protocol effect. So that's all. I want to acknowledge UTS and Australian Red Cross Lifeblood for giving me opportunity to do this research. And there are some selected references. And thank you.
Thank you, Morshidul. Do you have any questions? So I may actually start. Did you observe any censoring in your study? So someone who left the study or?
Yeah, so basically our outcome was mortality, and in the 45 and up study link data, we actually don't have any specific information that someone actually changed their residence to go somewhere, or some people may die from another state. So we don't have that information. But from other studies, what we found, the number is very small. So we actually ignored that.
Okay. Any other question? Yes, Alberto?
So in your estimation, you used the design, which is robust estimation for the errors to try to account for the potential of people repeating in different trials to kind of taking a person as a cluster. But did you actually take any other random effect, let's say, to take into account the trial as a cluster?
Did you hear the question, Moshe?
I could not hear it.
No, that's
properly.
fine. So I tried to repeat it. So you consider in the in your study, like a person has like a random effect for the person, but did you consider any other type of random effects? For example, a random effect for the trial. Did I do it correct?
Random effect for the trial?
Yeah, or any other type of random effect about the person, specific one.
Person specific random effect. I think if I had it a bit, so maybe it was they're asking something like, because people are repeatedly selected in each trial, so there may be correlation or something. So yeah,
so there could be like an effect specific for the trial, not only for the person.
Yeah, I actually have checked it. Yeah, maybe I haven't presented it here, but I actually checked it. So, and also I think if I had it correct, so I used one of the thing I used bootstrapping to calculate the confidence intervals, because people are repeatedly selected in each trial, so there might be correlation. So that's why I use bootstrapping, and also I think here I have written something. So yeah, I used robust variance estimators, as many individuals participated more than one trial, because there could be correlation from each observation. And also I use bootstrapping. I haven't showed it here, but to calculate the confidence intervals.
Okay, thank you. Anything else? Any other question? Okay, if not, let's thank you, Marsha, there again.
Thank you, Kevin.
And I would like to thank all the speakers of this afternoon. How amazing their presentations were. Well done for all your work. Well done. And I would also like to say that this is the first year since I joined the company that we have such a large group, but it was really fantastic to see your work. So very well done. You should be very proud of yourself. Now, what is going to happen is that the judges will deliberate in the room. There is a second refreshment just aside, like the first one. And we'll take around 10-15 minutes to deliberate, and then we'll do the award ceremony. So thank you very much. We'll be back in, let's say, 6:05.
Wait, actually, we'll have to get.
Ready?
Yes. Yes, I think I'm watching now. No more lights. Yes.
Sorry. There is an echo here, but I don't understand where it comes from.
Maybe Sally, we just need to mute. No, testing, no echo. Okay, good.
Okay, so we have deliberated, and I would like to call all the presenters here to receive their certificate of award for excellence in postgraduate research. So I'll call you your name, and then I'll like just ask you to come here, and then I'll give the names of the winners. So we have Matthew Sainsbury-Dale, Kieran Lucan, Jack Preston, sorry, like, yeah. Many pictures of myself. Morshad Rahman is online, but let's thank him again. Virginia Hay, Isha Karub, Annabelle Webb, Anant Mathur, Pakat Singh, and Emma Yuan. So let me say that the judges were really, really impressed with the quality of the presentations this year. So it was an amazing afternoon. Yes, sure. Where should I say?
It's up to you. In the middle. Squeezing. 1, 2, 3. Another one. Another one. Another one.
But we can have just a winner, or as in this case, we actually have 2 winners, and we can say that the judges were quite agreed easily on this. So let me thank and celebrate Matthew Sainsbury-Dale, and Jack Friesen. Many, many congratulations. Of course, many congratulations to all of you. Like, as I said, we were really impressed. So part you will be contacted by me and the treasurer and the secretary to organize the prize, but very well done, and very well done to everyone. Very well done. Thank you very much. Thank you. Let's say it with the call, that's right. Okay, so the day is not over yet. So so the next step is really the closing of the year for the branch of the society is our annual lecture. And it's really my pleasure to have Professor Sally Cripps from UTS to give the annual lecture this year. Of course, Sally doesn't need any presentation. Her work in so many fields is extremely known. So I'll let her start the presentation, and I would like to thank you again for agreeing to give it.
Well, thank you, Clara, and thanks everybody here, and what an enjoyable afternoon it has been.
Do you want any signal for anything or like?
No, I'm going to rush. Everybody's been sitting down so patiently. I'm going to rush through this. So, but no, it's been a wonderful afternoon listening, and what a high quality of presentations. And I think I think Clara said it at the beginning. It's a wonderful achievement to have been asked to be here. So congratulations to all participants, but particularly to our 2 stars. So what I would like to do is make an acknowledgement to country. I would like to acknowledge the Gadigal people of the Eora Nation, upon whose lands we are now gathered on, whether we're at UTS, so I wrote this for you too, or here at Sydney. And I would like to pay my respects to elders, both past and present, and acknowledge them as the traditional custodians of knowledge for this land. This is the moment you think, I hope it works, and it does. So look, today I'm going to give a talk about the art and science of causal inference, and I want to. Yep. Well, I would if I could sort of get it off presenter screen, but then you're going to see all my emails come up all over everywhere. So. Yes, it is. Yeah.
No, you can.
Yeah, but you might want to have not the presenter. Well, anyway, don't worry. They can see the presenter notes. I'm fine with that. Yeah. Okay. Yeah. Okay. So it's my pleasure to give a talk today. The talk is about the art and science of causal inference, and I'll talk about what I mean by that, and the implications for government policy making. The cartoon on the right is a serious situation that I've sat in lots when I've worked with government departments. Everybody's sitting down, everybody gets excited about big data, and then they don't know really what to do. In fact, they become almost petrified with the idea of how to make a decision. And hopefully by the end of this talk, I will convince you that actually I don't think big data is the answer to government decision making. I do think that it is about the ability for us as statisticians, data scientists, whatever you want to call us, to think carefully about the questions we want to answer, to come up with algorithms that can identify the useful information to answer a particular question to illuminate. So that is, I hope, going to be the big takeaway at the end, because I'd like to quote, paraphrase Nat Silver, where he said once that the amount of truth is approximately constant, irrespective of the volume of data we collect on it. And it is relevant information and identifying relevant information that I think is really important for governments. And so that's what I hope to be the takeaway message for today. Now, I'm going to start out with something slightly a little different. I'm going to say something about causal inference. I'm actually going to give you an example of something that is not about causal inference, just because it's very topical and it's a lot of fun. And one of the great things about ChatGPT is you can actually ask ChatGPT anything. And this time I asked ChatGPT to describe itself. And this is what it came back with. And it said, it's an example of narrow intelligence or narrow artificial intelligence. It goes on to say in bold, it's limited in that it lacks a true understanding of the text it generates. And, I want to pause there because I think that's a degree of insight and humility that is displayed by ChatGPT that most humans don't have. So I just want to say that that's a really interesting thing. The thing about ChatGPT that I do love, though, is that it sounds so knowledgeable. And so this is a quote that comes from an article written by a guy called Gary Marcus, where he asked it, why is crushed porcelain good to have in breast milk? And it came back with the answer that porcelain can help balance the nutritional content of milk, providing the infant with the nutrients they need to help grow and develop. Now the thing about ChatGPT is it does have no understanding, and that's why I brought it as an example. It is wonderful. I love ChatGPT. It is great at predicting. It is great at predicting the next word, but it has no understanding of the underlying process, and neither does it claim to. It is misused sometimes, but it has no understanding, and I think that the takeaway is that its objective function is fluency and not accuracy. And that once we understand that about ChatGPT and use it for what it is meant to be used for, it's an incredibly useful tool, but it is not a tool that we can use for causal inference. So, so now moving on to causal inference, I'm going to, run through sort of a gallop through examples of causal inference and what I've been working on for the last 5 to 7 years, and come to some conclusions. And so the first ones I'm going to start, I started out a lot of this causal inference because I was working with a bunch of people at Sydney Uni, the Earthbite group, about how landscapes and coral reefs form. Then I sort of moved from sort of physical sciences into life sciences, understanding obesity and maybe mental health. And again, all with the understanding of trying to figure out the causal pathways. And finally, I'm going to end up talking about the new space that I'm in, which is trying to figure out how we do this at a governmental scale. So moving away from isolated competencies to putting it all together in some systematic way, which can really help governments able to answer questions. And a huge thank you for Emma, because now I don't have to actually go into any of the explanations about graphical models. But, I'm going to couch it all in graphical models just because they're a really useful tool and a way to demonstrate things. And just so I'm not even going to do this now, but, I just had an example just in case people want to know. As Emma pointed out, graphical models are about two things. They're about firstly learning the structure, which encodes conditional independence. So there we can see that Y4, for example, is conditional on Y2 and Y3. It's conditionally independent of Y1. But we need to learn that structure, right? If we want to learn, we don't know whether it looked like that or whether it looks like this. So we've got two things that we want to learn. We want to learn the structure and the parameters associated with it. And we're going to be Bayesian just because that's what I am. So we're going to talk about how we can learn about structures and how learning structures is really about learning causal inference, sort of. I've said up there it's a useful but incomplete framework, and I'll get to why I think it's incomplete. But the models and the methods that we use, they're very useful things, but they're also tricky things. So just to say, we've got 3 chapters you've got to get through. First chapter that I'm going to talk about is when we know the structure, but we don't know the parameters associated with it. The second one is when we don't know the structure and the parameters. And the third one is where we neither know the structure nor the parameters nor the impact of any interventions that we're going to do. And that's 3 is the space that governments sort of sit at. Just to now go to sort of chapter 1, this is where the structure is known. And this is why I like graphical models. I'm going to talk about these 2 cases. Again, I just want to say this was work initially done with Dare, and I think, is Willem in the room? Yes. Hi, Willem. So there's Willem up there too, smiling down at you. But the great thing about being a statistician, of course, is you get to choose your collaborators, and I would advise you to choose them in places that have nice field work. So for example, one tree island on the Great Barrier Reef. So this was done in conjunction with these people. So the details don't matter. What does matter is here is a causal model, right? This causal model is actually just given by these ordinary differential equations. That they describe how reefs evolve. These are the generalized Lochte-Volterra equations. I can either represent this as the causal structure, this is the causal structure, or I can represent it as a graph. So once there is a correspondence between those series of equations and those graphs. So when I'm talking about causal models, when I have the physics actually tells me the causal structure. uncovering the physics. I'm assuming that the physics is right and I'm learning about the parameters. It's still a way of discovery, but it's not actually discovering the physics or the causal structure behind it, it's assuming it. And this is an example. Here they were interested in, the way in which sediment and water flow impacted on coral growths. We have priors, we connect it to likelihoods. This was some work that we did. It was very interesting. It turns out to be very, very difficult to explore posteriors in this situation, but I'm not going to go into that. That's just an example of using, a series of equations as a graph, as a vehicle for causal inference for the parameters. This was another example. Here we've got landscape evolution in the South Island of New Zealand. You've got these are essentially the Navier-Stokes equations. Again, here we've got a series of PDEs, but again, we're not discovering the causal structure. We're assuming that these things actually govern the way landscapes are formed. And the physical world, has lots of these types of physical models. And so the point of incorporating them is so that you get the benefit not only of the data. So in this particular instance, we have the current landscape in New Zealand. They wanted to find out what it looked like 1 million years ago. So that's a really hard problem. You've only got the data today and you want to infer back 1 million years what it looked like. And so the idea is you get the data today together with some sediments, and together with the physics, you can make inference about what happened, 1 million years ago. So it is these types of techniques are very useful, I think, in combining physics and data in the same way in order to learn, again, not to learn about the physics, but about the parameters of the physics. So there's the graphical model. There's a likelihood function. There's a posterior. So when I was thinking about exploring, posteriors, that is about as bad as they come. That has got, well, there are hundreds of modes, there's lots of peaks, and it's actually all induced by the fact that we've got continuous processes here that we've discretized, and it induces spurious structure in the likelihood. It actually took us 2 years to nail down what was actually going on here. And so it is still a super hard problem. We came up with a solution, and that was another paper, but that's sort of technical and I don't want to go there tonight. But even when we know the structure, things are difficult. But I'd now like to move to, well, what happens when we don't know the structure? And I'm going to be talking about 2 examples. First one was around childhood obesity. The second one was around mental health. Let me just say that the childhood obesity work was done with what's called the LSAC data. That's the longitudinal study of Australian children. Great data set. There are, since about 2003, every 2 years they update it. They've got each cohort's about 5,000 children. There are 7 waves of data. There's some of the data on that particular cohort. There is loads and loads of information in there. These are just a smattering of the variables. You've got all sorts of things right down to the characteristics of the child, what they eat, their activity, also the characteristics of the parent, what the socioeconomic group, their mental health of the parents, as well as the mental health of the child, and also the environment that the child lives in. And here we have no physics, right? We do not have a series of equations which tells us what that graph is. And this is one of the really hard areas in sort of statistical machine learning at the moment, I suppose, is to figure out how do you actually attach probabilities to a graph? Because here is one particular graph structure where I've got socioeconomic group feeding into maternal education and the parents' BMI, both feeding into the child's BMI. If there's only, that's another graph. There are only 4 nodes here, but even with 4 nodes, there's this, 1,536 graphs. Once we've got 25, we've got, more possible graphs than there are atoms in the universe. There's no way that you can do an exhaustive search over that. And in addition, the space is discrete, so there's no gradients that you can use. There are mechanisms around that, but this is a super hard problem. I'll talk about equivalence classes in a minute. So the challenge in learning graph structures has, there's a whole sway of literature now, mainly on the machine learning side, mainly in places like NeurIPS, but also in JASA and JCGS, where they're more sort of Monte Carlo based estimations. But essentially, it's a very difficult problem because there's something called equivalence classes, which I'll talk about in a minute. The size and the shape of the model space, if we've got gradients, things are easy. When things are just discrete, very difficult to optimize over such a large model space. And also, what graphs do is model conditional independence. And so when you've got both discrete and continuous random variables, figuring out what are good measures of dependence between those things is a non-trivial exercise. But I want to actually say here that, in this area of literature, particularly, I've got a lot of time for machine learners because I think that they've got a lot of energy and they explore and they do cool stuff. But sometimes they're a bit loosey-goosey with terminology. And one of them is they keep talking about learning graph structures as causal inference, but it's not really. It's telling us about conditional independence, which may be suggestive of causal inference, but it's not the same thing as causal inference. And causal inference is only possible if all relevant variables are in the graph, which is never the case, and even then only up to an equivalence class. So what do I mean by an equivalence class? These two graphs have exactly the same likelihood, right? So they have the same conditional independence structure. They will give you the same likelihood, but they have very different causal inference. In one, you've got maternal education going to socioeconomic status, in the other one, the reverse is true. So untangling that is something that is really difficult. So that's something to be aware of. So these are the sorts of research that's been done in this space now. There's a lot of stuff happening in the machine learning literature, and machine learners, they love gradients. And so what they do is they just love gradients. So they get the discrete space and they project it into a continuous space and do the optimization in the continuous space, which gets them the optimum, but it gives them very poor estimates of the uncertainties around graphs. So putting probabilities over graphs, which is really important for decision makers. So they miss that. But they're pretty impressive actually in what they've been able to do when you consider what a difficult problem this really is. There are other techniques, these belong more to the stats literature, which are also very impressive. They're better sampling based methods to explore it. And I've given some references of articles that have come out recently that I think have done a very good job of doing this. So I'm just going to skip that. I'll skip to some of the results. So this was for the childhood obesity. This is the child BMI. It's floating around. It's this red diamond here. These are for 2 to 3 year olds, right? So just to give a bit of background, the blue lines with the arrows indicate positive dependencies. In the direction where the arrow is, the orange lines are negative dependencies, and in the direction where the bar is at the end. The coloured circles mean that these are nodes that are ancestors, the terminology is, of this final child node. So in other words, we're wanting to know what leads to a child's level of body mass index or childhood obesity. This one shows clearly that it's parent 1 and parent 2's BMI. This one BWZ is the birth weight. But what you also see here is that, at the centre of it is this socioeconomic group, which is really driving a lot of behaviours in this particular network. So this is an example of, and of course this is just one of several billion possible networks. This is the most likely, but one of several billion that are possible, right? So, and as we go forward, you can see this is for 4 and 5 year olds. It's starting to change. 5 and 6, 7 and 8, and by the time they become to 9 and 10, you start to see this other sort of. You've still got socioeconomic group as being the really important indicator, but but also you're getting this second central node emerging around sleep. And this is the one to show your sons, if you have any who are young boys, because this one, panel A is for boys and panel B is for girls. And what this shows is that if we look at what the causal pathways start doing for boys at about this age, we've got socioeconomic group. It's so lower socioeconomic groups watch more TV. The more TV, the more electronic games. The more electronic games, the less exercise, and the less exercise, sleep, and so on. It finally feeds down into, well, the exercise here goes directly to the child's BMI. So this starts to give you a structure. And this work was actually sponsored originally by the Paul Ramsay Foundation, who were interested in medical problems. And as a result of this, they shifted their emphasis from medical to actually looking at more upstream causes, because it sort of suggests, it's not to say that we shouldn't work at making these more proximal causes, such as playing games, electronic games, is not, important to try and curb that. But if we're not addressing these really upstream issues, we're sort of tinkering around the edges rather than addressing what really happens. And so this then, some of this work got the attention of the New South Wales government, and I will then go on to say about that. Interestingly, you can see that same causal pathway, or that link between electronic games and lack of activity, and finally down to the BMI is not there for the girls. So you see that this is the causal pathway for boys. So this then got us thinking about, so how can we, obviously if these graphs are different for girls and boys, they're probably different for a whole variety of reasons. So how can we actually come up with a model that tries to say, well, there may be different causal structures for different groups of the population, and this has really important implications for governments wanting to know which intervention to use under which conditions. So, do you intervene in a school to do this for this group may be totally different for 16-year-old girls who live in Glebe than it is for 10-year-old boys who are living in Burke. So these types of interventions, which you want to know these causal structures, because the causal structure tells you what you should be intervening on, but it may be very different for different groups. So we came up with a model that was sort of looking at, okay, I'm now going to split all these factors into one of two categories: those that I can modify, and we'll put them in the structure, the network, because I can actually pull a handle on those sorts of things, and those things that I can't modify, right? Because I want to make them they're like exogenous variables. And effectively what we did was have a mixture model where we said that there were these signatures of networks, but the signature networks depended on factors such as gender, such as socioeconomic groups, that we couldn't change. And this we did this with sort of the Brain and Mind Centre at Sydney Uni, because they were looking at mental health. And so, the variables that were potentially modifiable, they're the Ys, and then the ones that were the Zs were the ones that we put in the mixing function. And I will just cut pretty much straight to what happens here. So this is what happened with this group when the most likely number of components in this particular data set was a mixture of, 2. And the biggest, interestingly, the biggest predictor of whether you were in model 1 or model 2 was not the things that we actually put in the Z box, which was, they weren't things like gender or traumatic event, well they were slightly, and mental history. The thing, the big differentiator was suicidal thoughts. So if a child had suicidal thoughts, they were in mixture group 2 versus mixture group 1. And these are the marginal graphs. So these graphs represent the marginal probabilities of those without directions, as opposed to the map estimates, which are the actual directed graphs above. And so one of the really important things that we took out of this, and it was a really interesting piece of work from the brain and mind center point of view was that people often think, oh, well, depression leads to lack of functioning, but what we actually found was that functioning leads to depression rather than the other way around. So the inability to be able to function had led them to the depressive thoughts that led then to a whole variety of things. Again, showing the power of these techniques, but the difficulty in doing it. Okay. So we're on a roll. I'm in time and you're going to be fed very shortly. So we're up to chapter 3. So, and here, so, you know, this is in a static world, right? This is where I've got the data and I'm not actually looking at the impact of what I've done. I'm actually just trying to figure out what that particular data says. From a government point of view, that's not really what they want to do. They want to know what would happen if I intervened. If I do this policy, how does that whole thing change? And so that then becomes a question of, it's like a multiple, hypothesis test. You're not just looking at whether there's been a shift in the mean, but you're looking at, has that whole structure of the way things are related together changed as a result of the intervention for the government? And this is work that then led us to the Department of Education, who very kindly are partnering with us to figure out what educational innovations help young Australians finish school well. We're very thankful for a very large donation from the Paul Ramsay Foundation that is funding this work to try and figure out, as a result of the work that we did around the childhood obesity, they then shifted their focus back to socioeconomic group, and in particular, you know, what can we do around education to reduce the gap? What you will find is over the last 10 or 20 years, you know, actually Australia's educational, you know, high school completion rates have been going up, but in disadvantaged communities, they've been going down at a faster rate than they've been going up in it. So the gap is widening. And so the impetus here is to try and figure out what's going on. And I've just got a toy diagram here. A great example of a good use of large language models is, you know, because we're Bayesian, we have to have a prior around a graph. They can be very useful for summarizing literature and constructing priors in that way. I mean, noticing that they are priors, I haven't put, this is the most likely one of the priors. Obviously, there's a lot of uncertainty around this, but so here, a lot of the emphasis is on looking at what predicts high school completion rates. A is attendance, and it's pretty obvious that attendance is really important, but it's sort of measuring the same thing, if you know what I mean. You know, you can't finish high school if you don't show up to the exam. So it's again a bit like the body mass index case, when if you just focus on making kids turn up and you're not addressing these other issues that are surrounding it, such as, for example, the length. These are mainly rural communities, the distance they live from the school, their sense of community belonging, etc. Then you might, you know, you're not going to have the sustained impact that you want. As I said, you know, graphs are great, but they only do conditional independence. To establish a true causal relationship, you need an experiment or an intervention or whatever you want to do it, or calling it a support initiative, because you're not allowed to use, and I understand their point of view, that in the Department of Education, you are not allowed to use, we are not experimenting on children. And no, it's true. And then there's this, so some of the latest stuff in graphs is around, okay, so how do you then jointly model the impact of an intervention? And it's not too difficult if you can, there's this thing called do calculus, right? So here is community belonging. Effectively, what you're doing is replacing a node here that has a distribution attached to it to a fixed value, in other words, with a Dirac delta function, but you proceed as before, right? So you're estimating the before and after, while knowing, you see that, for example, once you have this Dirac delta function, you know, and you're fixing community belonging, then distance cannot be a parent of it for obvious reasons, because you're controlling it to be that. Neither can the CI is golly, I've forgotten. This is student confidence and this is community involvement. That's right, community involvement. That can't be apparent either. So the idea is that you fix this and then you learn how does the network change. And that's a great idea, right? Because it enables you to see what would happen to the whole network if you fix something. You know, what's wrong with that idea? Well, it's pretty obvious. You actually can't just intervene and give everybody a sense of community belonging. This is not a randomized control trial. You can't give somebody a dose. All you can do is put in a policy in place and hope that you get some result. So you have to have a model that says, okay, so I put this policy in, I haven't fixed a random variable to anything. I'm not sure which one of those nodes it's going to impact. I'm not sure by how much it's going to impact those nodes. They are the things that I'm modelling. And so that's what this is a model of. This is saying, so these are now drawn so that they're sort of variations on a circle. What it's trying to say, this H is just an indicator variable, which is we're probabilistically allowing any one of those nodes to be impacted by the intervention. And so this is where the research is at the moment. And I think it's a really exciting area of research, although it's difficult because, you know, when you're searching over such a large space and when so much is at stake, I think it can be quite daunting. So I hope what I'm trying to get at is I think there's so many good things going on in data science, and I would put ChatGPT up there with one of those good things, but nothing, I've come to the conclusion that nothing really beats a great sort of systematic way of thinking about how to learn properly from data. And I think that's where, as statisticians, we excel, and we still excel at that. And so I've got this is from isolated competencies to systems thinking. And I think the systems thinking is something we can borrow from this computer science community, actually. Whoops. And I've said here, hang on, what happened then? I don't know. Okay. So what we need is we need knowledge learning systems that start with developing algorithms that tell us what we don't know. And again, this is where statistics come into its own, because we actually want to use these algorithms or measures of uncertainty to value pieces of future information. So if I'm uncertain, then I can ask myself, if I had that piece of information, by how much would that reduce my uncertainty? And then that becomes the value of that piece of information. And then we can use the digital revolution to help us gather that information in a sequential fashion that helps us answer the specific question that we ask. And so we wrote an article about this, and it was in the conversation, so we had to sort of tailor it to something that was sort of readable for the general public. And so, you know, and a lot of these ideas I've got from working with people in computer science, particularly from the robotics people, because this is how a robot operates. So, you know, so here is what does the moon's surface look like? So you send a robot to the moon, the designers give it a prior belief, along with the confidence in that belief. And the confidence in the belief, or the uncertainty, is the crucial thing. The robot lands, it faces a decision which way to go, and it goes in the direction that will maximize its learning. It goes to the new place, it gets new information, it updates what it believes about what the moon looks like, and it proceeds in this way. And it explores the moon in the most efficient way possible with the fewest, not the most data, but the fewest relevant pieces of data. And, you know, so this was the idea that we took to the government and the Department of Education, and it's the same question. So, you know, does a mentorship program improve school outcomes? Well, what does the current, you know, form prior beliefs? What does it say? What does community, what does the expert opinion say? So figure out an intervention to implement and to which community, by those that if you had that information, you would maximally learn about the impact of that intervention. Implement the intervention, gather data, and repeat. So it's exactly the same as the robot exploring the moon. It's harder because there's more things in play, but the idea behind it, the systems thinking behind it, which I'm putting up here, is exactly the same. So this is what we're doing. This is actually Thrive. This is what we're doing with the Department of Education, is putting in place these systems which will help maximally learn about what will improve educational outcomes for school children in New South Wales and hopefully in Australia later on. And that's where I'd like to leave it, and any questions. Thank you very much.